dark matter and cosmic structures. Furthermore, the Boötes void serves as a reminder of the universe's inhomogeneous nature, where galaxies are not evenly distributed but are instead arranged in a vast cosmic web. This web consists of high-density filaments and nodes, separated by voids that vary in size and shape. The discovery of such structures has led to refinements in numerical simulations of the universe, allowing astrophysicists to test predictions about galaxy formation, dark matter distribution, and cosmic expansion. Some theories suggest that the Boötes void may be the result of multiple smaller voids merging over time, creating an exceptionally large underdense region. This hypothesis is supported by the presence of a few isolated galaxies within the void, which may have formed in residual filaments that failed to collapse into larger structures. These galaxies offer a rare opportunity to study star formation and galactic evolution in an environment relatively free from external gravitational influences. In addition to its scientific significance, the Boötes void has also captured the imagination of the public, inspiring speculation about whether such vast emptiness could be indicative of unknown cosmic phenomena. While some have suggested that large voids might be associated with exotic physics, such as modifications to general relativity or even artificial megastructures built by advanced civilizations, mainstream astrophysical research attributes their existence to well-understood processes of cosmic evolution. As observations of the large-scale universe continue to improve with next-generation telescopes and advanced computational modeling, voids like the Boötes void will remain essential to refining our understanding of cosmology. Future studies may provide even deeper insights into the role of dark matter, dark energy, and the fundamental forces shaping the universe. The Boötes void stands as a remarkable anomaly in the cosmic landscape, not only due to its sheer scale but also because of the scientific questions it raises about the large-scale structure of the universe. Spanning roughly 0.27% of the observable universe's diameter, this void defies intuitive expectations about the uniform distribution of matter. If the universe were completely homogeneous, regions as empty as the Boötes void would be highly improbable. Yet, its existence aligns with our current understanding of structure formation, demonstrating how gravity amplifies tiny density fluctuations over cosmic time. The formation of the Boötes void is tied to the broader mechanisms of cosmic evolution. In the early universe, small quantum fluctuations in the density of matter led to the formation of the cosmic web, a network of filaments and nodes connected by gravity. Regions with slightly higher densities attracted more matter, growing into galaxies and clusters, while less dense regions expanded into voids due to the gravitational pull of surrounding structures. Over billions of years, these underdense areas have become even emptier as matter continues to migrate toward the denser filaments. Cosmological simulations suggest that voids like the Boötes void emerge naturally from the lambda-CDM model of the universe. The void likely formed as smaller voids merged, reinforcing its extreme emptiness. This hierarchical merging process is analogous to how galaxy clusters grow over time. Interestingly, voids expand at a slightly faster rate than their surrounding regions because they contain less matter and experience weaker gravitational pull. This accelerated expansion makes voids unique laboratories for testing dark energy, the mysterious force driving the universe's expansion. Despite its name, the Boötes void is not completely devoid of galaxies. A sparse population of approximately 60 galaxies has been identified within its vast expanse, a remarkably low number compared to the expected density of several thousand galaxies for a region of this size. These galaxies are not randomly distributed, they appear to form small chains or filaments, suggesting that residual structure remains within the void. Some astrophysicists propose that these galaxies are survivors of an earlier cosmic epoch, having formed in regions where the density was just high enough to sustain gravitational collapse. One of the most studied galaxies in the Boötes void is MCG plus 0102-015, a relatively isolated system located near the void center. The properties of such galaxies make them interesting targets for studying star formation under conditions of extreme isolation. Unlike galaxies in denser regions, which experience frequent mergers and interactions, void galaxies evolve with minimal external influence, providing a cleaner environment to study the natural progression of stellar and galactic evolution. The Boötes void and other large cosmic voids serve as crucial testbeds for studying dark matter and dark energy. Since voids are regions where the effects of ordinary matter are minimal, they allow astrophysicists to probe the subtle gravitational influences of dark matter. Some theories suggest that voids could enhance our understanding of modified gravity models, which propose alternatives to dark matter by tweaking the laws of gravity on large scales. Additionally, voids provide insights into the nature of dark energy. The accelerated expansion of voids is consistent with the standard lambda-CDM model, but alternative explanations, such as scalar field theories or modifications to general relativity, could manifest in void dynamics. By studying how galaxies within voids move relative to their surroundings, scientists can constrain competing theories about cosmic expansion. When the Boötes void was first discovered, it seemed to challenge the standard model of cosmology, raising questions about whether such an extreme void could arise naturally. However, subsequent studies have identified numerous other large voids, including the Uranus supervoid and the northern local supervoid. Some of these voids are comparable in scale, suggesting that the Boötes void, while extraordinary, is not entirely unique. The discovery of these additional voids has strengthened the statistical case for their existence. According to simulations, cosmic voids should make up a significant fraction of the universe's volume, even though they contain relatively little mass. In fact, voids may occupy as much as 80% of the universe's volume, with matter concentrated in the filaments and clusters that form the cosmic web. This perspective fundamentally changes how we view the universe, not as a homogeneously distributed sea of galaxies, but as a vast network dominated by emptiness. Another intriguing aspect of cosmic voids is their potential role in neutrino physics. Neutrinos, the elusive subatomic particles that barely interact with matter, are thought to play a role in shaping large-scale structures. Since voids are extremely low-density environments, they provide an ideal setting to test how neutrinos contribute to cosmic expansion and structure formation. Some speculative theories even propose that voids like the Boötes void could be associated with more exotic physics. For example, certain alternative cosmologies suggest that voids may be remnants of primordial quantum fluctuations or even regions where different physical laws apply. While mainstream cosmology explains voids through gravitational evolution, the sheer size of the Boötes void has led some to wonder whether it could hint at undiscovered cosmic phenomena. The Boötes void has also captured the imagination of the public and inspired various speculative ideas. Some have likened its vast emptiness to the hypothetical concept of a Kardashev Type III civilization, a civilization advanced enough to manipulate entire galaxies. While no evidence supports the idea that the void was artificially created, its extreme nature has fueled sci-fi discussions about cosmic megastructures, intergalactic engineering, and the possibility of dead zones in the universe. Philosophically, the Boötes void serves as a reminder of the vastness and complexity of the cosmos. The existence of such immense empty regions challenges our understanding of cosmic structure, compelling us to refine our models of galaxy formation and evolution. It also highlights the contrast between dense galaxy clusters teeming with activity and isolated voids where galaxies are scarce and interactions are minimal. With advancements in observational astronomy, the study of voids like the Boötes void is entering a new era. Upcoming surveys, such as those conducted by the Vera C. Rubin Observatory and the Euclid Space Telescope, will provide unprecedented insights into the large-scale distribution of voids and their role in cosmic evolution. High-resolution maps of the cosmic web will allow scientists to study the detailed structure of voids, including how their boundaries interact with surrounding filaments. Future research will also explore how voids influence cosmic microwave background (CMB) radiation. Some studies suggest that voids create subtle temperature fluctuations in the CMB due to the integrated Sachs-Wolf effect, which arises from the gravitational interaction of photons with evolving cosmic structures. By analyzing these effects, scientists may gain further insights into the nature of dark energy and the evolution of the universe. Additionally, upcoming gravitational wave observatories may provide indirect insights into the nature of voids. Since voids are low-density environments with minimal astrophysical noise, they could serve as ideal locations for detecting exotic phenomena, such as potential signatures of cosmic strings or primordial black holes. The Boötes void remains one of the most fascinating and enigmatic structures in the cosmos. Its immense scale, sparse galaxy population, and implications for cosmology make it a crucial subject of study. Whether viewed as a natural outcome of structure formation, a probe for dark energy and dark matter, or a philosophical reminder of cosmic emptiness, the Boötes void continues to inspire curiosity in scientific investigation. As observational techniques improve, our understanding of voids will deepen, shedding new light on the fundamental forces shaping the universe. The Boötes void's role in the larger cosmic landscape extends beyond its immediate structure, influencing the gravitational environment of the surrounding universe. Its vast underdensity creates a unique dynamical effect, subtly altering the movement of nearby galaxies and filaments. Because voids have less mass than their surroundings, they exert weaker gravitational attraction, allowing the structures on their periphery to expand outward at a faster rate. This phenomenon is sometimes referred to as void expansion and plays a critical role in shaping the cosmic web over billions of years. The gravitational influence of large voids like the Boötes void has been observed through peculiar velocity studies, which measure the deviations of galaxy motions from the expected Hubble flow. Galaxies on the outskirts of voids tend to experience an outward acceleration as they move away from the underdense region toward denser filaments and clusters. This motion can be detected through redshift surveys, providing an independent method for studying the large-scale distribution of matter. The study of void dynamics offers an indirect way to probe dark matter, as the rate of void expansion depends on the underlying mass distribution, including both visible and invisible components. The interaction between voids and their surroundings also affects the properties of galaxies that reside within or near them. Galaxies within voids tend to have lower star formation rates compared to those in denser environments, primarily due to the limited availability of intergalactic gas. In contrast, galaxies on the edges of voids often show signs of enhanced star formation, likely triggered by interactions as they move toward denser filaments. This suggests that void boundaries act as transition zones where galaxies undergo significant evolutionary changes, making them valuable targets for studying environmental effects on galactic development. The study of voids also intersects with research on the cosmic microwave background, CMB, the faint relic radiation from the Big Bang. Large underdense regions like the Boötes void can imprint subtle temperature fluctuations on the CMB through the integrated Sachs-Wolf (ISW) effect. As CMB photons pass through a void, they experience a slight energy shift due to the evolving gravitational potential of the underdense region. This effect provides another way to test theories of dark energy, as different models predict varying strengths of the ISW signal. Recent studies have explored whether the Boötes void contributes to the anomalous CMB cold spot, an unusually large and cold region in the cosmic microwave background, though the connection remains uncertain. In addition to their role in observational cosmology, voids have become a crucial aspect of numerical simulations aimed at understanding the formation and evolution of large-scale structures. Cosmologists use high-resolution simulations to recreate voids in virtual universes, adjusting parameters such as dark energy density, dark matter interactions, and initial cosmic fluctuations. These simulations confirm that voids naturally arise as a consequence of structure formation and that their properties can serve as a diagnostic tool for testing alternative cosmological models. Some speculative theories even suggest that voids could be linked to modifications of gravity at cosmic scales, potentially offering an alternative explanation to the lambda-CDM model. Another intriguing aspect of void studies is their potential impact on the search for exotic astrophysical objects. Because voids are largely free from strong gravitational interactions, they provide an ideal environment for detecting faint astrophysical signals that might otherwise be obscured in denser regions. Some researchers have proposed that voids could harbor primordial black holes, hypothetical remnants from the early universe that might contribute to dark matter. The lack of competing astrophysical noise in voids also makes them an interesting region for searching for hypothetical signatures of axions, weakly interacting particles that could solve outstanding problems in particle physics and cosmology. Beyond astrophysics, the Boötes void serves as a profound reminder of the universe's extreme contrasts, highlighting the balance between structure and emptiness on cosmic scales. While dense galaxy clusters form the bustling hubs of cosmic activity, voids represent the silent, vast regions where the gravitational influences are minimized, allowing a clearer view into the fundamental workings of cosmic expansion. The existence of such massive voids challenges our perception of the universe, illustrating how even emptiness plays an essential role in shaping its overall structure. Observations of the Boötes void continue to improve with advances in telescope technology. Upcoming instruments, such as the Square Kilometre Array, SKA, will provide higher resolution maps of large-scale structure, offering deeper insights into the distribution and properties of voids. Meanwhile, future space missions dedicated to studying dark energy, such as NASA's Nancy Grace Roman Space Telescope, will help refine our understanding of void expansion and its connection to the accelerated growth of the universe. The combination of observational surveys and theoretical models will ensure that voids remain at the forefront of cosmological research, pushing the boundaries of our knowledge about the fundamental nature of space and time. The possibility that voids could serve as natural laboratories for testing unconventional physics remains an open question. Some speculative ideas suggest that voids might be regions where deviations from standard physics become more pronounced. For example, certain quantum gravity theories predict that spacetime may behave differently in extremely low-density environments, potentially offering clues about the unification of gravity in quantum mechanics. While these ideas remain highly theoretical, they underscore the importance of studying extreme cosmic environments, where fundamental physics may reveal unexpected properties. In the broader context of cosmic evolution, voids like the Boötes void remind us that the universe is not a uniform sea of galaxies but a dynamic interplay between matter-rich regions and vast cosmic deserts. These immense voids, often overlooked in favor of more visually striking galaxy clusters, hold some of the most profound secrets about the forces shaping the cosmos. Their study not only enhances our understanding of cosmic structure formation but also opens new pathways for exploring the deepest questions in physics, from the nature of dark energy to the possible existence of hidden dimensions beyond our current perception. As observational capabilities continue to advance, the Boötes void and similar cosmic structures will provide an ever-expanding source of information about the past, present, and future of the universe. With each new discovery, the boundaries of our understanding shift, revealing that even in the vast emptiness of space, there are stories yet to be told. The vast emptiness of the Boötes void not only challenges our understanding of large-scale cosmic structure but also raises deeper questions about the fundamental nature of the universe. The presence of such an enormous underdense region suggests that voids may play a more active role in cosmic evolution than previously thought. While they are often seen as mere byproducts of structure formation, their unique properties, such as their accelerated expansion, weak gravitational fields, and influence on cosmic flows, may offer new insights into both standard and exotic physics. One of the most intriguing consequences of cosmic voids is their potential impact on time dilation effects in general relativity. Some theoretical studies suggest that the expansion of voids could lead to subtle relativistic effects, affecting the passage of time differently compared to denser regions of space. While these effects would be minuscule compared to those caused by strong gravitational fields, they could contribute to our broader understanding of how spacetime behaves under varying density conditions. If voids exhibit even slight deviations from the expected expansion rates, this could hint at new physics beyond the current lambda-CDM framework. Additionally, voids may act as natural magnifying lenses for rare cosmological phenomena. Since voids contain fewer foreground objects and less gravitational lensing compared to dense galaxy clusters, they offer a relatively clean view of distant quasars, cosmic explosions, and even potential transient events such as fast radio bursts, FRBs. The lack of competing gravitational distortions in void regions makes them ideal locations for detecting faint signals from the early universe, possibly revealing information about primordial black holes, ancient quasars, or even unexplored aspects of cosmic evolution. The Boötes void's extreme scale also raises questions about whether it could be linked to primordial fluctuations from the early universe. Cosmic inflation, the rapid expansion that occurred just after the Big Bang, is thought to have left behind small density variations that later evolved into the large-scale structures we see today. However, the size of the Boötes void suggests that some regions of the universe may have experienced much larger fluctuations than previously modeled. If the void originated from an unusually low-density fluctuation in the early universe, it could offer clues about inflationary physics and the conditions that governed the very first moments of cosmic history. Beyond observational cosmology, voids also provide a unique testing ground for dark matter interactions. While most dark matter research focuses on dense galaxy clusters where its gravitational effects are strongest, voids present the opposite scenario, a region where dark matter is expected to be present but in significantly lower densities. If dark matter interacts with itself or with ordinary matter in ways beyond standard gravitational attraction, voids may be the best places to observe such subtle effects. Some speculative models suggest that dark matter could have different properties in low-density environments, possibly even decaying or transitioning into exotic particles over vast timescales. The study of void galaxies, which evolve in near isolation, could help refine these theories by providing clues about how dark matter behaves in regions with minimal external gravitational influences. Another important area of research involves the potential relationship between cosmic voids and the missing baryon problem, the unresolved question of why a significant fraction of the universe's normal, baryonic, matter remains undetected. While much of this missing matter is believed to exist in the warm-hot intergalactic medium, WIM, a diffuse, ionized gas that permeates the cosmic web, voids may hold crucial evidence of its distribution. Because voids contain fewer galaxies and less luminous matter, they provide an ideal environment for detecting WIM filaments, which are otherwise difficult to observe due to their faint nature. High-resolution X-ray observations could help trace these elusive filaments, shedding light on the overall matter budget of the universe. The Boötes void also serves as a natural laboratory for studying alternative gravity models. Some modified gravity theories predict that cosmic voids should expand at rates slightly different from those expected under general relativity. Precise measurements of void expansion using large-scale surveys like the Dark Energy Spectroscopic Instrument, DESI, could help test these predictions and potentially reveal deviations from Einsteinian gravity. If such deviations were detected, they could hint at new physics governing the fundamental nature of spacetime, possibly pointing toward the existence of additional forces or extra dimensions. The study of voids is entering a new era with increasingly advanced observational techniques. The upcoming Vera C. Rubin Observatory, set to conduct the Legacy Survey of Space and Time, LSST, will provide unprecedented maps of large-scale structures, allowing for detailed investigations of void distributions and their impact on cosmic flows. Meanwhile, the European Space Agency's Euclid mission will offer high-precision measurements of cosmic expansion, helping to refine our understanding of void dynamics and their role in the evolution of dark energy. As more voids are mapped in detail, astronomers are beginning to classify them based on their unique properties. Some voids appear nearly spherical, while others have highly irregular shapes, suggesting that different formation mechanisms may be at play. There is also growing evidence that some voids may be nested within larger voids, creating a complex hierarchy of underdense regions. Understanding this hierarchy could provide further insights into how matter is distributed on the largest scales and how different cosmic environments shape the formation of galaxies and other structures. The philosophical implications of cosmic voids are equally profound. They challenge the human perception of space as something inherently full, demonstrating that the universe is dominated not by galaxies but by vast stretches of near-nothingness. This realization shifts the focus from studying what is present to understanding what is absent, making voids just as critical to cosmology as the galaxies and clusters that define the cosmic web. The study of emptiness, rather than mere absence, becomes a central theme in the exploration of the cosmos, revealing that voids are not simply empty spaces but active participants in the grand cosmic evolution. As technology improves and our observational reach extends deeper into the universe, the Boötes void will remain one of the most intriguing and enigmatic regions in the cosmos. Whether through its potential role in testing new physics, its impact on cosmic structure formation, or its ability to serve as a natural observatory for the deepest mysteries of space, the study of voids will continue to expand our knowledge of the universe's origins, composition, and ultimate fate. The Boötes void, like other cosmic voids, is not merely an empty region but an evolving structure with complex interactions at its boundaries. The outskirts of the void, where its vast emptiness meets the denser filaments of the cosmic web, serve as transition zones where galaxies experience environmental shifts. These boundary regions, sometimes referred to as void walls, are where gravitational influences from surrounding structures exert pressure on the expanding void. This dynamic interaction results in what is known as void evacuation, a process where matter is gradually pulled toward denser regions, leaving behind an ever-growing empty space. The continued expansion of voids is one of the mechanisms that contribute to the large-scale movement of galaxies, shaping the overall distribution of matter in the universe. Interestingly, void walls may also act as cosmic reservoirs for intergalactic gas. While the interior of voids is largely devoid of star-forming material, their boundaries contain diffuse filaments of hydrogen and other elements, remnants of the primordial gas that formed the first galaxies. These filaments can serve as fuel for star formation in void galaxies, albeit at a much slower rate than in denser environments. Some of the few galaxies found inside voids appear to be slowly accreting gas from these filaments, suggesting that, despite their isolation, void galaxies continue to evolve, albeit on longer timescales. One of the most intriguing questions surrounding cosmic voids is whether they could harbor exotic forms of matter or energy not yet detected in standard cosmology. Some theoretical models propose that voids might be ideal locations for studying quintessence, a dynamic form of dark energy that could vary in intensity across different regions of space. Unlike the cosmological constant model of dark energy, which assumes a uniform energy density throughout the universe, quintessence theories suggest that dark energy may have a more complex behavior, with possible variations in void environments. If voids exhibit expansion rates inconsistent with standard predictions, this could be an indirect sign of new physics governing the nature of dark energy. Another speculative idea is that voids could serve as cosmic laboratories for testing alternative interpretations of gravity. Some modified gravity theories predict that voids should expand at different rates compared to what is expected under general relativity. These effects are difficult to detect in denser regions due to the complex interplay of gravitational forces, but voids, being relatively free of such complications, provide a clearer setting to test such hypotheses. If deviations from expected void expansion rates were observed, they could hint at a deeper understanding of gravity at cosmic scales. Recent studies have also suggested that voids might be important in addressing anomalies in the cosmic microwave background, CMB. The cold spot, a large region of slightly lower temperature detected in the CMB, has been the subject of intense debate. Some researchers have proposed that a large underdense region, possibly a supervoid, could be responsible for this anomaly through the integrated Sachs-Wolf effect, in which photons passing through an evolving void experience slight shifts in energy. While the Boötes void itself is not directly linked to the cold spot, its existence supports the idea that such massive voids can influence the cosmic radiation left over from the Big Bang. Observationally, the study of voids has benefited from advancements in redshift surveys, which map the three-dimensional positions of galaxies across vast cosmic distances. Large-scale surveys such as the Sloan Digital Sky Survey, SDSS, and the upcoming Euclid mission are providing increasingly detailed maps of the cosmic web, allowing astronomers to identify and analyze void structures with unprecedented accuracy. These surveys have revealed that voids are not uniform in shape. Some are nearly spherical, while others are elongated or irregular, suggesting a complex interplay of gravitational forces that shape their evolution. Void galaxies, those rare systems found in the depths of cosmic voids, continue to be a subject of interest due to their unique properties. Unlike galaxies in clusters, which experience frequent mergers and gravitational interactions, void galaxies evolve in relative isolation, making them excellent test cases for studying internal galactic processes without external interference. Some void galaxies exhibit unusually high rotational speeds, suggesting that they may contain higher proportions of dark matter compared to their counterparts in denser regions. This has led to speculation that the low-density environment of voids may influence how dark matter behaves on galactic scales. The search for faint dwarf galaxies within voids is another promising avenue of research. Dwarf galaxies are thought to be the building blocks of larger galaxies, and their distribution within voids could provide insights into early galaxy formation. Some simulations predict that voids should contain numerous faint dwarf galaxies that have failed to grow into larger systems due to the lack of external gravitational influences. Detecting these elusive galaxies requires deep imaging surveys and sensitive spectroscopic observations, which are becoming increasingly feasible with next-generation telescopes. The implications of cosmic voids extend beyond astrophysics into fundamental physics, particularly in the search for alternative explanations of cosmic acceleration. While dark energy is currently the leading explanation for the universe's accelerating expansion, some theories propose that the apparent acceleration could be an illusion caused by the large-scale distribution of voids and filaments. In these models, light traveling through underdense regions experiences different gravitational effects compared to light traveling through denser clusters, leading to observational effects that mimic cosmic acceleration. If such models were confirmed, they could reshape our understanding of the universe's expansion and the fundamental forces governing it. As the study of voids progresses, it is becoming clear that these vast cosmic regions are not mere empty spaces but dynamic components of the universe's large-scale structure. Whether through their influence on galaxy evolution, their role in testing dark energy and modified gravity, or their potential connection to fundamental physics, voids represent a frontier in cosmological research. Future observational campaigns and theoretical studies will continue to refine our understanding of voids, potentially revealing new and unexpected aspects of the universe. The Boötes void remains one of the most striking examples of these immense structures, serving as both a scientific challenge and a source of wonder. Its extreme scale, sparse galaxy population, and potential implications for cosmic evolution ensure that it will remain an important subject of study in the years to come. As our observational tools improve and our theoretical models become more sophisticated, the study of cosmic voids will undoubtedly lead to deeper insights into the nature of space, time, and the underlying fabric of the cosmos. The Boötes void and other cosmic voids not only provide a unique perspective on the large-scale distribution of matter but also raise fundamental questions about the initial conditions of the universe. One of the most intriguing ideas is whether voids could contain clues about deviations from the standard inflationary model. Cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang, is believed to have imprinted subtle density fluctuations across the early universe. While these fluctuations led to the formation of galaxies and clusters, they also contributed to the emergence of voids. However, the Boötes void's exceptional size has led some researchers to wonder whether it could be the result of an unusually large primordial underdensity, one that deviates from standard Gaussian fluctuations predicted by inflation. If such a deviation were confirmed, it could have profound implications for our understanding of the early universe. Some alternative inflationary models predict the existence of large-scale non-Gaussian features, meaning that the density fluctuations responsible for galaxy formation may not have been purely random but instead influenced by unknown physics during the earliest moments of cosmic history. Detecting such anomalies within void structures could provide insights into the conditions that existed before the universe became transparent to radiation, offering a glimpse into physics beyond the observable horizon. In addition to their potential connection to early universe physics, voids may also serve as windows into the nature of the cosmic neutrino background. Neutrinos, nearly massless particles that rarely interact with matter, were once thought to have little impact on cosmic structure formation. However, their tiny but non-zero mass means that they move at relativistic speeds early in the universe, suppressing the formation of small-scale structures while allowing larger structures like voids to expand more freely. By studying the properties of voids, cosmologists can place tighter constraints on the total neutrino mass and determine whether exotic neutrino properties, such as sterile neutrinos or interactions beyond the standard model, could play a role in shaping the cosmos. The influence of voids extends even further into the study of dark matter, particularly in understanding its distribution and behavior under extreme conditions. Most observational efforts to study dark matter focus on galaxy clusters, where gravitational lensing provides direct evidence of unseen mass. However, voids offer an entirely different approach. Rather than studying how dark matter concentrates, researchers can examine how it behaves in regions of near emptiness. If dark matter has non-gravitational interactions or exhibits properties such as self-interaction or decay over cosmic time, voids may be one of the best places to detect such effects. Any anomalous gravitational behavior within voids compared to denser regions could hint at deviations from the conventional cold-dark matter paradigm. Another speculative but intriguing possibility is that voids might act as conduits for detecting hypothetical cosmic structures such as domain walls or cosmic strings. These relics from the early universe, if they exist, could manifest as large-scale gravitational anomalies within voids, influencing the motion of galaxies near void boundaries. While no direct evidence for such structures has been found, voids provide a natural testing ground for these ideas, as they are relatively undisturbed environments where even subtle gravitational effects could be more easily detected. On an observational level, upcoming missions such as the Vera C. Rubin Observatory and the Euclid satellite will provide increasingly detailed maps of the cosmic web, allowing researchers to refine void catalogs and study their properties with unprecedented precision. These surveys will help determine whether void expansion rates match theoretical predictions or if there are unexpected variations that could hint at new physics. High-resolution weak lensing studies, which measure tiny distortions in background light due to intervening mass distributions, will also allow for more accurate mapping of void interiors, potentially revealing substructures that were previously undetectable. The potential for voids to reveal new aspects of physics is not limited to fundamental cosmology. There are also implications for astrophysical processes occurring within them. While void galaxies are rare, those that do exist offer an opportunity to study star formation in environments with minimal external influences. Some void galaxies exhibit unusually high rates of star formation compared to expectations, leading to speculation that their isolation may result in a prolonged retention of gas, allowing them to sustain star formation over longer timescales. Studying these galaxies could provide insights into the role of environmental factors in galactic evolution and whether void galaxies represent an earlier stage in the formation of larger systems. Beyond individual galaxies, the intergalactic medium, IGM, within voids may also hold important clues about cosmic evolution. While the IGM in denser regions is often ionized by radiation from active galaxies and quasars, voids may contain pockets of neutral hydrogen that have remained relatively undisturbed since the cosmic dawn. Detecting such pristine gas could offer a unique opportunity to study the conditions of the early universe, potentially revealing information about the reionization epoch, the period when the first galaxies and quasars ionized the surrounding hydrogen, transforming the universe into its present state. The Boötes void, despite its remoteness and emptiness, serves as a reminder that the universe is shaped not only by what is present but also by what is absent. Voids represent the silent, expanding structures that influence the motion of galaxies, the behavior of dark matter, and the properties of the cosmic expansion itself. They are not simply regions of nothingness but active participants in the evolution of the cosmos, shaping the grand narrative of structure formation in ways that are still being uncovered. As new observational techniques and theoretical models continue to refine our understanding, voids will remain at the forefront of cosmological research. Their study has the potential to unlock new perspectives on everything from the nature of dark energy to the possibility of physics beyond the standard model. The Boötes void, as one of the most extreme examples of such structures, will undoubtedly continue to inspire scientific inquiry, challenging our understanding of the universe while revealing the hidden forces that govern its vast and mysterious expanse. The continued investigation of the Boötes void also challenges us to rethink the role of statistical outliers in cosmology. In a universe governed by probabilistic processes, where density fluctuations from quantum origins were stretched to macroscopic scales by inflation, extreme structures like the Boötes void are not necessarily violations of the model but rather its most striking predictions. These rare cosmic events, occurring at the far tails of probability distributions, are essential for testing the robustness of our cosmological framework. If structures like the Boötes void appear more frequently or exhibit properties inconsistent with predictions from simulations based on lambda-CDM, it could signal the need for new physics or a refinement of initial condition assumptions. There is also a growing interest in exploring the relationship between voids and cosmic topology, the study of the universe's global geometric properties. Some cosmologists have proposed that the large-scale arrangement of voids, filaments, and clusters could reflect deeper aspects of the universe's shape and connectivity, potentially even hinting at a non-trivial topology. If the universe wraps around itself in higher dimensions, as proposed in some compact topology models, patterns in the distribution of voids could offer indirect evidence. Analyzing the large-scale coherence, orientation, and alignment of voids might one day help answer the profound question of whether the universe is finite or infinite in extent. Moreover, the acoustic signatures of voids, particularly their imprint on baryon acoustic oscillations, BAO, offer another tool for cosmologists. BAOs are relic patterns of sound waves that moved through the early universe's plasma before recombination. These waves left a subtle but detectable imprint on the distribution of galaxies and matter. While most BAO studies focus on galaxy clusters, voids also contain this signal, albeit inverted. Analyzing the BAO signal in voids provides a complementary and independent measure of the expansion history of the universe, allowing researchers to further constrain the equation of state of dark energy and test the consistency of cosmological parameters. In the computational realm, the modeling of voids has become increasingly sophisticated. Modern cosmological simulations can now resolve both the vast scales of voids and the finer details of the galaxies within them. These simulations incorporate not only gravitational dynamics but also complex baryonic processes such as gas cooling, star formation, and feedback from supernovae and black holes. By comparing observed void properties with those from simulated universes, scientists are able to fine-tune models and rule out parameters or processes that fail to reproduce the real universe. In this way, voids act as powerful calibration tools for refining our most fundamental models of cosmic evolution. Another dimension to void research lies in the emerging field of void lensing. Though voids are underdense, their cumulative gravitational effect can still influence the path of light traveling through or near them. This weak lensing effect is extremely subtle, far less dramatic than the strong lensing seen near massive clusters, but it is measurable with precise data. Detecting and analyzing void lensing helps map the distribution of mass in and around voids, offering indirect insights into the dark matter component that dominates the universe's mass budget. Combined with galaxy dynamics and redshift space distortions, void lensing adds another layer to our ability to probe gravity and structure formation. On the frontier of observational astrophysics, new techniques are being developed to probe the gas content within voids. Instruments capable of detecting faint Lyman alpha absorption features from background quasars are helping to reveal the distribution of neutral hydrogen and ionized gas in these vast regions. By mapping how this gas evolves over cosmic time, researchers can reconstruct the history of matter flow from the early universe to the present day. These observations also test predictions from hydrodynamical simulations and provide a clearer picture of how the intergalactic medium behaves under different environmental conditions. From a philosophical and anthropic perspective, the Boötes void adds depth to the contemplation of our cosmic position. Humanity exists in a region of the universe where galaxies, stars, and heavy elements are abundant, a place where life, as we know it, has the necessary ingredients to arise. But most of the universe, as evidenced by regions like the Boötes void, is vastly different, quiet, cold, nearly empty, and almost entirely sterile. The existence of such immense voids underscores the rarity and fragility of the conditions that allow life to flourish. It raises existential questions about cosmic isolation and the likelihood of other intelligent civilizations emerging elsewhere, especially in such barren zones. This has even sparked speculation in the context of the Fermi paradox, the question of why, given the vastness of the universe, we have not yet observed signs of extraterrestrial intelligence. Some thinkers have wondered whether large voids could represent deserts in the galactic ecosystem, where the emergence of complex life is statistically improbable due to environmental isolation. In such a view, the Boötes void might not only be physically empty but biologically empty as well, a reminder that life-supporting conditions are concentrated in only select corners of the cosmic web. In the end, the Boötes void remains a canvas onto which cosmologists, astronomers, physicists, and philosophers alike project some of their deepest questions. It is a structure born from gravitational evolution, shaped by primordial fluctuations, expanded by the unseen forces of dark energy, and now studied with tools crafted by the most advanced scientific instruments humanity has ever created. Its silence, its stillness, and its scale speak to the immensity of the cosmos and the continuing journey of discovery that propels our understanding of it forward. As researchers delve deeper into the Boötes void and its analogues, attention is increasingly turning to the role these immense underdense regions may play in defining the boundaries of cosmic evolution itself. Rather than being passive absences of matter, voids may act as dynamic components within the cosmic web, influencing not only their immediate surroundings but also the statistical behavior of structure formation on the largest scales. One emerging area of research involves the concept of cosmic back reaction, the idea that local inhomogeneities, like voids and clusters, could cumulatively influence the average expansion rate of the universe. While standard cosmology assumes that small-scale variations average out over large volumes, some researchers argue that this averaging may not be perfect. In this view, the prevalence and growth of voids could subtly alter the observed acceleration of cosmic expansion. Although this idea remains controversial and mathematically complex, the Boötes void offers a real-world laboratory for evaluating such effects and testing whether the standard assumptions about cosmic averaging hold at all scales. Furthermore, voids like Boötes are essential for understanding the full life cycle of matter in the universe. Galaxies located within or near voids provide rare insights into how isolated systems evolve. Without frequent mergers or environmental interactions, these galaxies often retain more primordial characteristics, such as simpler morphologies, extended Hi gas disks, and lower metallicities. By examining these isolated systems, astronomers can reconstruct the conditions of the early universe and trace the relatively undisturbed pathways of galaxy growth. In this sense, void galaxies may serve as time capsules, preserving evolutionary histories that are erased or overwritten in more crowded cosmic neighborhoods. The chemical composition of void galaxies also contributes to this picture. Spectroscopic studies have revealed that void galaxies tend to have fewer heavy elements, metals, than their counterparts in clusters and groups. This lower metallicity supports the idea that void galaxies experience slower and more gradual star formation, allowing for a more pristine environment in which the early conditions of the universe are reflected in the present. This makes them valuable targets for chemical evolution models, helping scientists understand how elements are produced, recycled, and distributed across time and space. There is also a practical observational benefit to the study of voids. They provide clear lines of sight through the universe. In denser regions, the intergalactic medium is often crowded with gas, dust, and intervening galaxies that obscure or distort the light from distant sources. Voids, by contrast, offer relatively unobstructed pathways through space, enabling more precise observations of high redshift objects, gravitational waves, and background radiation. These low-opacity windows into the cosmos can be used to study quasars, gamma-ray bursts, and the faint glows of the early universe, free from much of the foreground interference that complicates observations elsewhere. In the context of dark energy research, voids present one of the most sensitive tools available for detecting deviations from standard cosmological behavior. Because voids are effectively pressureless environments, the way in which they expand and evolve is governed primarily by the geometry of space and the properties of dark energy. If dark energy changes over time or behaves differently across different environments, these differences should manifest most clearly in void dynamics. Ongoing efforts to measure the sizes, shapes, and expansion rates of voids over cosmic time aim to detect these effects and constrain possible variations in the dark energy equation of state. Meanwhile, machine learning and artificial intelligence are increasingly being applied to the classification and analysis of cosmic voids. With the enormous datasets generated by current and future galaxy surveys, traditional methods of void identification are being supplemented by automated algorithms that can detect subtle void structures across vast cosmic volumes. These tools are also capable of identifying correlations between void properties and other cosmic observables, such as galaxy bias, halo occupation distribution, and redshift space distortions. By integrating observational data with simulation outputs, AI is opening new avenues for high-precision void cosmology. The sheer psychological impact of the Boötes void continues to echo beyond the domain of science. For many, it symbolizes the overwhelming vastness of the universe and the humbling realization that most of cosmic space is profoundly, deeply empty. Philosophers and writers have drawn inspiration from the idea that even in a universe filled with light and matter, it is the dark and silent spaces that dominate. The Boötes void, stretching for hundreds of millions of light-years with only a handful of galaxies scattered within, becomes a metaphor for the loneliness of existence, or, alternatively, for the elegant simplicity of nature's grand design. In science fiction and speculative thought, voids have become associated with the unknown. Some fictional works imagine them as hiding places for ancient civilizations, interdimensional rifts, or relics of failed universes. While such ideas lie outside the boundaries of empirical science, they reflect a human tendency to imbue the cosmos with meaning, to see in the emptiness not just the absence of matter, but the potential for mystery, transformation, or revelation. Returning to the realm of science, it's important to note that the boundaries of voids are not static. They grow and evolve over time, driven by the flow of matter away from their interiors and toward denser regions. This movement, called large-scale cosmic flow, is not only a key prediction of cosmological models but also a measurable phenomenon. By observing the velocities of galaxies near void edges, astronomers can map the gravitational influence of voids and verify how closely these flows align with theoretical predictions. Deviations in these flow patterns could signal the influence of unknown forces or particles, offering yet another potential window into undiscovered aspects of cosmic physics. Ultimately, the Boötes void challenges us not just to look deeper into the structure of the universe, but to refine our methods, stretch our theories, and confront our assumptions. It reminds us that what we do not see may be as important as what we do, that the gaps in the cosmic web, the dark spaces between the stars, and the vast volumes between galaxies are not empty of meaning, but filled with clues to the deepest workings of reality. The Boötes void continues to serve as a gravitational and conceptual anchor in the growing exploration of cosmic voids, illuminating the hidden architectures of the universe. While traditional cosmological efforts have focused on galaxy clusters, quasars, and other bright, energetic regions, voids offer an inverse perspective, one that foregrounds the role of absence, silence, and expansion in the formation and evolution of cosmic structures. As voids grow, they contribute to the overall anisotropy of the cosmic web. This evolving asymmetry introduces subtle, large-scale features that may influence everything from galaxy spin alignments to the directionality of cosmic flows. Recent studies suggest that the orientations of galaxies and even the spin vectors of dark matter halos can be correlated with their position relative to nearby voids. This void-induced alignment effect hints at a deeper interconnectedness between the geometry of space and the evolution of individual cosmic systems. If confirmed, such findings could redefine the way cosmologists think about the environment-dependent evolution of galaxies, lending support to the idea that even in the vast emptiness of voids, structural memory and directional imprinting persist. These patterns could also help to explain certain anomalies in cosmic isotropy. While the cosmological principle assumes the universe is homogeneous and isotropic on large scales, increasingly precise observations have revealed potential large-scale asymmetries in the CMB and galaxy distributions. Though still under debate, these cosmic hemispheric asymmetries may be linked to the statistical presence or configuration of enormous voids and superclusters across the observable universe. The Boötes void, by virtue of its exceptional scale, has become a reference point in these discussions, a test case for understanding whether large-scale inhomogeneities may hint at a deeper anisotropic fabric to spacetime. Another emerging frontier is the study of the intervoid regions, the connective zones between multiple voids. These tenuous corridors of extremely low-density matter are among the least understood environments in the universe. Simulations predict that these ultra-diffuse bridges may contain traces of dark matter filaments or warm-hot baryonic material too faint to detect through traditional means. By targeting regions between large voids, astronomers hope to detect the faint signatures of the missing baryons, thought to reside in these nearly invisible structures. This endeavor merges void cosmology with the broader search for the hidden components of the cosmic inventory. The intersection of void studies with time-domain astronomy is also a promising field. Because voids are gravitationally quiet and contain few astrophysical sources, they may provide ideal backgrounds for the detection of transient phenomena. Fast radio bursts, high-energy neutrino events, or even hypothetical technosignatures, if they occur within or traverse void regions, may be more easily identifiable due to the minimal noise and interference. Monitoring these dark expanses could reveal not only new classes of cosmic phenomena but also clarify the nature and distribution of known transients. Meanwhile, cosmological simulations are entering a new phase of resolution and complexity, allowing for the modeling of voids not just as simple underdensities but as rich, dynamic systems with substructure, thermal histories, and internal flows. The so-called void hierarchy is now being explored, the idea that voids contain smaller voids within them, nested across scales, forming a fractal-like structure in space. This multi-layered emptiness defies earlier assumptions that voids are relatively featureless. Instead, a void may have its own internal web, its own filaments, walls, and nodes, albeit on a much more subtle scale. This hierarchy of emptiness could have implications for entropy and information distribution in the universe. Some theorists have speculated that voids, by being the end points of structure evolution, regions where matter flows out and rarely returns, could serve as natural entropic sinks. If so, then voids may play a role in the universe's thermodynamic arrow of time, slowly accumulating low-density, low-temperature matter and radiation over billions of years. As galaxies age, stars burn out, and black holes evaporate, it's conceivable that more of the universe will begin to resemble the Boötes void, not just in structure, but in thermodynamic character. In this far-future scenario, voids become the model, not the exception. As cosmic acceleration continues to separate gravitationally bound systems, isolated galaxies and galaxy groups may drift toward a state of permanent cosmic solitude, surrounded by ever-growing voids. The Boötes void, then, could be seen as a prototype for the late universe, a preview of the conditions that will dominate when star formation has ceased, matter has dispersed, and even light from distant systems can no longer traverse the widening gulfs of expanding space. Even on these philosophical and temporal scales, the Boötes void provokes reflection. It is a boundary between presence and absence, between the luminous and the hidden, between the known and the unknowable. And yet, through the lens of science, it becomes a map, not of nothingness, but of subtle, elegant processes unfolding in silence and at unimaginable scale. The study of voids is, in many ways, the study of space itself, its geometry, its structure, its evolution. And it reveals, again and again, that emptiness is not the absence of structure, it is the structure. Within the vast hollowness of the Boötes void lies a wealth of information about the forces that sculpted the universe, about the past and future of matter and energy, and about the limits of our own understanding. As astronomers continue to map the cosmos in ever greater detail, the Boötes void will remain a profound frontier, not just in physical space, but in intellectual space as well. A frontier where darkness is not ignorance, but invitation. In the end, the Boötes void is not merely a vast emptiness, it is a cosmic mirror, reflecting the universe's deepest processes and quietest truths. Its silence speaks of structure, its darkness of evolution. As one of the universe's grandest voids, it reminds us that even in the absence of matter, there is profound meaning. The study of such places continues to expand our understanding, not just of the cosmos, but of our place within it.
Uranus is one of the most mysterious and fascinating planets in our solar system, a world that continues to puzzle scientists and inspire curiosity. It is the seventh planet from the Sun, orbiting at an average distance of about 2.87 billion kilometers, 1.78 billion miles. This icy giant stands out not only for its composition and unique features, but also for the challenges it poses to our understanding of planetary science. Discovered in 1781 by William Herschel, Uranus was the first planet found with the aid of a telescope. Unlike the 5 planets visible to the naked eye, Uranus marked the expansion of our cosmic horizons. Initially thought to be a star or comet, it was later confirmed as a planet, fundamentally changing how humanity viewed the solar system. One of the most striking characteristics of Uranus is its extreme axial tilt of 98 degrees. Unlike other planets, which spin more or less upright relative to their orbits, Uranus essentially rolls along its orbit, spinning on its side. This unique orientation creates extreme seasonal variations. Each pole experiences 42 Earth years of continuous sunlight, followed by 42 years of darkness. Scientists are still trying to fully understand the origin of this tilt, with the prevailing theory suggesting a massive collision with an Earth-sized object early in the planet's history. Uranus is classified as an ice giant, along with its sibling Neptune. While Jupiter and Saturn are dominated by hydrogen and helium, Uranus has a higher proportion of ices, such as water, ammonia, and methane in its interior. This methane is also responsible for the planet's pale blue color, as it absorbs red light and reflects blue. However, the planet's color is less vivid compared to Neptune's, possibly due to differences in atmospheric haze. Beneath Uranus' calm appearance lies a dynamic and turbulent atmosphere. The planet experiences supersonic winds reaching speeds of up to 900 kilometers per hour, 560 miles per hour. Its temperature drops to a frigid -224 degrees Celsius, -371 degrees Fahrenheit, making it the coldest planet in the solar system. Paradoxically, despite its icy nature, Uranus emits very little internal heat compared to other planets. This lack of heat flow is another mystery, as it suggests a unique thermal evolution. Uranus also has a complex magnetic field, which is significantly tilted from its rotational axis and offset from the planet's center. Unlike Earth's relatively symmetrical magnetic field, Uranus' magnetosphere is lopsided and highly dynamic, causing its magnetic poles to wander unpredictably. This field interacts with the solar wind to produce unusual auroras, which differ greatly from those observed on Earth and Jupiter. The planet is surrounded by a system of 13 faint rings and 27 known moons, all named after characters from Shakespeare and Alexander Pope's works. The rings are dark and narrow, composed of icy and rocky particles, possibly remnants of a shattered moon or comet. Among its moons, Titania and Oberon are the largest, with intriguing surfaces marked by canyons, impact craters, and possibly signs of subsurface activity. Exploration of Uranus has been limited to the flyby of NASA's Voyager 2 spacecraft in 1986. During its brief encounter, Voyager 2 provided a wealth of data, revealing details about the planet's atmosphere, rings, and moons. However, much remains unknown. Unlike Jupiter and Saturn, Uranus has not been revisited by any spacecraft, leaving it as one of the least studied planets in the solar system. Future missions to Uranus are a high priority for planetary scientists. Such missions could provide insights into the formation and evolution of ice giants, which are among the most common types of planets in our galaxy. Understanding Uranus could also shed light on exoplanets that share similar characteristics. Key goals include investigating its internal structure, atmospheric dynamics, magnetic field, and potential for subsurface oceans on its moons. Uranus challenges our understanding of planetary systems. Its unique characteristics, from its extreme tilt to its dynamic weather and mysterious interior, make it a compelling target for exploration. As technology advances and space agencies plan new missions, the icy giant may finally reveal its secrets, enriching our knowledge of not only the solar system but also the diversity of planets in the universe. Uranus, the seventh planet from the Sun, is one of the most intriguing and enigmatic worlds in our solar system. This ice giant, located approximately 2.87 billion kilometers, 178 billion miles, from the Sun, defies conventional planetary norms with its unique features, baffling scientists and captivating astronomers for centuries. Discovered in 1781 by the German-born British astronomer William Herschel, Uranus was the first planet identified with the aid of a telescope. Its discovery was revolutionary, expanding the known boundaries of the solar system and marking the beginning of modern planetary astronomy. Initially thought to be a comet or star, its true nature as a planet was confirmed through careful observation, altering humanity's understanding of the cosmos. One of Uranus's most striking features is its extreme axial tilt of approximately 98 degrees. Unlike any other planet in the solar system, Uranus spins almost entirely on its side. This means its poles face the Sun at different points in its orbit, leading to extreme and prolonged seasons. Each pole experiences 42 Earth years of continuous sunlight followed by 42 years of darkness, creating a climatic dynamic unlike anything on Earth. Scientists theorize that this tilt resulted from a colossal collision with an Earth-sized object during the early stages of the planet's formation. Uranus is classified as an ice giant, along with its neighbor Neptune. While Jupiter and Saturn are predominantly composed of hydrogen and helium, Uranus has a higher concentration of ices, which include water, ammonia, and methane. These substances exist under extreme pressure and temperatures within the planet's interior, contributing to its unique characteristics. The methane in its upper atmosphere absorbs red light, giving Uranus its pale blue color. However, its hue is less vibrant than Neptune's, possibly due to differences in atmospheric haze or chemical composition. The atmosphere of Uranus is a harsh, dynamic environment, with winds reaching speeds of up to 900 kilometers per hour, 560 miles per hour. It is the coldest planetary atmosphere in the solar system, with minimum temperatures plunging to -224 degrees Celsius, -371 degrees Fahrenheit. This frigid environment raises intriguing questions about the planet's thermal history, as Uranus emits surprisingly little internal heat compared to other giant planets. Another fascinating aspect of Uranus is its complex and asymmetric magnetic field. Unlike Earth, where the magnetic field is relatively aligned with the planet's rotational axis, Uranus's magnetic field is tilted by about 59 degrees and offset from its center. This lopsided and irregular field creates unique auroras and interacts with the solar wind in ways that remain poorly understood. Voyager 2, the only spacecraft to visit Uranus, revealed this peculiar magnetic environment during its 1986 flyby, leaving scientists eager for more detailed exploration. Uranus is surrounded by a faint ring system, consisting of 13 known rings primarily composed of dark particles. These rings are far less prominent than Saturn's, but they are fascinating in their own right, possibly formed from shattered moons or remnants of ancient collisions. Beyond its rings, Uranus has 27 known moons, all named after characters from Shakespearean plays and Alexander Pope's works. The largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, are icy worlds with intriguing geological features, including deep canyons, impact craters, and possibly even subsurface oceans. The moons of Uranus hold particular interest for astrobiologists. Some, like Miranda and Titania, may harbor subsurface oceans beneath their icy crusts. If confirmed, these oceans could contain the necessary conditions for life, such as liquid water and organic molecules. Understanding these environments is a key goal for future exploration, as they could shed light on the potential for habitability elsewhere in the solar system. Despite its scientific significance, Uranus remains one of the least studied planets in the solar system. Voyager 2's brief flyby provided valuable data, but it only scratched the surface of understanding this enigmatic world. Scientists advocate for a dedicated mission to Uranus, which could include an orbiter and atmospheric probe to investigate its composition, magnetic field, weather patterns, and moons in detail. Such a mission would also enhance our understanding of ice giants, which are among the most common types of planets discovered in other star systems. The study of Uranus is not just about understanding one planet. It is about gaining insights into the broader processes that govern planetary formation and evolution. Ice giants like Uranus challenge our models of planetary interiors, atmospheres, and magnetic fields. Moreover, their study could provide crucial context for interpreting observations of exoplanets with similar characteristics. In the future, missions to Uranus could revolutionize our knowledge of the outer solar system. An orbiter equipped with advanced instruments could map the planet's interior, analyze its atmosphere, and study its moons and rings in unprecedented detail. Such a mission would likely require innovative technologies, including nuclear-powered systems to sustain operations in the dim sunlight so far from the sun. Uranus embodies the mysteries of the outer solar system, challenging scientists to think beyond conventional models and explore the unknown. Its extreme tilt, frigid temperatures, complex magnetic field, and potential subsurface oceans make it a compelling target for future exploration. By unlocking the secrets of Uranus, humanity may uncover fundamental truths about the formation and evolution of planetary systems, both in our solar system and beyond. Exploration of Uranus also holds immense potential for understanding planetary systems beyond our own. Over the past 2 decades, thousands of exoplanets have been discovered orbiting other stars, and a significant fraction of these are ice giant analogs, planets similar in size and mass to Uranus and Neptune. Studying Uranus in detail can provide a critical reference point for interpreting data from these distant worlds, helping scientists determine their atmospheric composition, internal structures, and potential for hosting life. One of the most puzzling aspects of Uranus is its lack of significant heat emission. Unlike Jupiter, Saturn, and Neptune, which radiate more heat than they absorb from the sun, Uranus emits almost no detectable internal heat. This raises questions about the planet's formation and thermal evolution. Some theories suggest that Uranus experienced a cataclysmic impact during its early history, which not only caused its extreme axial tilt but also disrupted its internal heat distribution, effectively locking in its cold state. Understanding this anomaly could reveal new insights into the thermal dynamics of ice giants and their formation in the protoplanetary disk. The planet's atmosphere is another area of intense scientific curiosity. Beneath its calm blue exterior lies a complex system of storms, winds, and chemical reactions. Observations from Earth-based telescopes and the Hubble Space Telescope have detected bright spots and cloud systems that indicate dynamic weather patterns. These features suggest that, despite its low internal heat, Uranus has an active atmosphere driven by seasonal changes and possibly unknown processes occurring deep within the planet. Future missions equipped with high-resolution imaging and spectroscopy could provide a more detailed picture of these atmospheric phenomena. The rings and moons of Uranus are equally compelling targets for exploration. Unlike the dense, icy rings of Saturn, Uranus's rings are dark and sparse, likely composed of organic-rich materials. Their origin remains a mystery. Were they formed from ancient collisions, or are they remnants of the planet's early accretion process? Answering these questions could illuminate the processes that shaped the outer solar system. Uranus's moons, particularly Titania and Oberon, are prime candidates for detailed study. These moons are large enough to be considered dwarf planets if they orbited the Sun independently. Their surfaces, marked by craters, rifts, and other geological features, hint at a complex history of tectonic and possibly cryovolcanic activity. Subsurface oceans may exist on some of these moons, maintained by residual heat and the presence of antifreeze compounds like ammonia. Exploring these moons could provide invaluable clues about the conditions required for life and the potential for habitable environments on icy worlds. Moreover, Uranus's magnetic field adds another layer of complexity to its study. The tilted, offset nature of the field suggests that the planet's dynamo, a mechanism in its interior that generates the magnetic field, is fundamentally different from that of Earth or the gas giants. Understanding how this dynamo operates under the extreme pressures and compositions of Uranus's interior could expand our knowledge of planetary magnetism across a wide range of celestial bodies. The technology needed to explore Uranus poses its own set of challenges. Given its vast distance from the Sun, any spacecraft sent to Uranus must rely on nuclear-powered systems, such as radioisotope thermoelectric generators, RTGs, to function effectively in the dim light and frigid temperatures of the outer solar system. Communications delays of about 2.7 hours each way will also require advanced autonomous systems capable of conducting scientific operations without constant input from Earth. NASA and other space agencies are actively considering missions to Uranus, recognizing its scientific importance. A dedicated orbiter and atmospheric probe could revolutionize our understanding of ice giants, building on the limited but tantalizing data provided by Voyager 2. By diving into Uranus's atmosphere, the probe could directly measure its composition, temperature, and pressure, providing data that is impossible to obtain from Earth. Meanwhile, an orbiter could map the planet's magnetic field, study its rings and moons, and monitor its atmospheric activity over time. Exploring Uranus is about more than just unraveling the mysteries of a single planet. It is a journey to understand the processes that shape the diversity of planetary systems across the galaxy. Ice giants like Uranus are thought to form in specific regions of protoplanetary disks, migrating over time to their current positions. By studying Uranus, we can refine our models of how planets form, migrate, and interact within their systems. In the coming decades, as humanity ventures further into the cosmos, Uranus will likely play a central role in expanding our knowledge of planetary science. Its unique characteristics, extreme axial tilt, icy composition, unusual magnetic field, and dynamic moons, make it a natural laboratory for testing theories and uncovering new phenomena. By exploring this distant world, we not only deepen our understanding of our own solar system, but also gain a glimpse into the nature of countless other planetary systems that populate the universe. Uranus reminds us that even in our own cosmic backyard, there is so much left to discover. Each step toward its exploration brings us closer to answering fundamental questions about the origins and workings of planets, the potential for life beyond Earth, and the intricate dynamics of the cosmos itself. This icy giant, silent and distant, holds the keys to unlocking some of the most profound mysteries of existence. The potential for Uranus to unlock profound cosmic mysteries cannot be overstated. Despite its silent and distant presence, it holds answers to questions that extend far beyond our solar system. To truly grasp the significance of Uranus, we must delve deeper into what its exploration could reveal, not only about itself but about the nature of planetary systems and the broader universe. One of the most exciting prospects in studying Uranus lies in its connection to the field of comparative planetology. Ice giants like Uranus and Neptune occupy a middle ground between terrestrial planets, such as Earth and Mars, and the gas giants Jupiter and Saturn. This intermediate category bridges the gap in our understanding of planetary formation and evolution. By comparing Uranus with other planets, scientists can refine their theories about how planets develop over time, why their compositions vary, and how they interact with their environments. For instance, the atmospheric dynamics of Uranus are a puzzle waiting to be solved. Unlike Jupiter and Saturn, whose atmospheres are dominated by powerful storms and heat-driven convection, Uranus appears deceptively calm on the surface. However, its atmosphere is far from static. Infrared observations reveal complex cloud structures, likely composed of methane, ammonia, and water ice. These clouds, combined with supersonic winds and temperature inversions, hint at hidden processes driving atmospheric circulation. Understanding these dynamics could help scientists model atmospheres on distant exoplanets with similar compositions. Speaking of exoplanets, Uranus is an invaluable analog for studying planets beyond our solar system. Many of the exoplanets discovered to date fall into a category known as mini-Neptunes or sub-Neptunes, which are similar in size and composition to Uranus and Neptune. These planets are among the most common types in our galaxy, yet they remain poorly understood because we lack detailed observations of similar planets in our own system. By studying Uranus, we gain a Rosetta Stone for interpreting data on these distant worlds, helping us unlock their atmospheric compositions, internal structures, and potential for habitability. Another fascinating aspect of Uranus is its potential to host unique chemistry within its interior. The extreme pressures and temperatures inside Uranus may create exotic states of matter, such as superionic water, where hydrogen ions move freely within a lattice of oxygen atoms. This phase of water, which behaves like a conductor, could play a crucial role in generating Uranus's unusual magnetic field. Additionally, carbon within Uranus's interior might form diamonds, which could sink to the core in a diamond rain phenomenon. These processes are not only captivating in their own right, but also provide critical insights into how materials behave under extreme conditions. Uranus's moons add yet another layer of intrigue to its study. Each of its major moons, Titania, Oberon, Ariel, Umbriel, and Miranda, offers a unique geological story. Miranda, for instance, has one of the most unusual and varied surfaces in the solar system, featuring massive cliffs, ridges, and possibly evidence of cryovolcanism. Titania and Oberon, the largest moons, may harbor subsurface oceans, raising the possibility of environments capable of supporting microbial life. If confirmed, these moons could join the ranks of other ocean worlds in the solar system, such as Europa and Enceladus, as prime targets in the search for life. To explore Uranus effectively, future missions will need to leverage the latest advancements in technology and engineering. An orbiter equipped with instruments such as spectrometers, magnetometers, and imaging systems could conduct detailed surveys of the planet and its moons. A descent probe could directly sample the planet's atmosphere, providing data on its composition, temperature, and pressure gradients. Such a mission would represent a monumental leap in our understanding, comparable to the groundbreaking studies of Jupiter by the Juno spacecraft or Saturn by the Cassini-Huygens mission. The logistical challenges of reaching Uranus are significant but not insurmountable. Its vast distance from the Sun means that spacecraft must be equipped with power sources like radioisotope thermoelectric generators, RTGs, which can operate in low-light conditions. The journey itself, lasting 10 to 15 years depending on the launch window and trajectory, requires precise planning and execution. However, the scientific payoff would be immense, offering decades of data to analyze and interpret. Looking ahead, Uranus could also become a stepping stone for future exploration of the outer solar system. A mission to Uranus would serve as a testbed for technologies and techniques needed to explore even more distant worlds, such as Neptune and its largest moon, Triton. It could also pave the way for interstellar exploration by demonstrating our ability to operate spacecraft effectively at extreme distances from the Sun. Ultimately, Uranus reminds us of the boundless potential for discovery that lies within our own cosmic neighborhood. Every detail we uncover about this enigmatic planet, its atmosphere, interior, magnetic field, rings, and moons, adds another piece to the puzzle of how planets form, evolve, and interact. In studying Uranus, we not only deepen our understanding of the solar system, but also take steps toward answering some of the most profound questions about the universe. How common are planets like Earth? Could life exist elsewhere? What forces shape the cosmos we inhabit? The exploration of Uranus is not just an academic pursuit. It is a testament to humanity's unyielding curiosity and drive to explore the unknown. As we continue to push the boundaries of knowledge, Uranus stands as a beacon of possibility, inviting us to uncover its secrets and, in doing so, illuminate the mysteries of the universe. The journey to Uranus is not just a scientific endeavor, but also a philosophical one. It represents our quest to understand our place in the cosmos and our connection to the processes that have shaped the solar system. Uranus, with its peculiarities and mysteries, offers a unique lens through which we can view the broader dynamics of planetary systems. One of the most profound questions that Uranus could help answer concerns the formation of ice giants. While the gas giants Jupiter and Saturn formed closer to the Sun and accumulated massive hydrogen and helium atmospheres, ice giants like Uranus and Neptune likely formed farther out, where water, ammonia, and methane could condense into solid ice. These volatile-rich planets might have formed their cores first, later capturing a thinner atmosphere of hydrogen and helium. But why did Uranus and Neptune stop growing, while Jupiter and Saturn continued to accumulate gas? And how did their migration to their current positions influence the development of the entire solar system? By studying Uranus's internal structure, scientists hope to uncover clues about this process. Current models suggest that the planet's interior is composed of a rocky core, surrounded by a thick layer of water, ammonia, and methane ices, and enveloped by a relatively thin hydrogen-helium atmosphere. However, there are significant uncertainties. For example, Uranus's lack of internal heat emission raises questions about its energy balance. Did an ancient collision disrupt its interior and scatter its heat outward, leaving it colder than expected? Understanding Uranus's thermal history is essential for piecing together the puzzle of its formation. Uranus's moons, too, hold keys to the planet's past. These natural satellites are not just passive companions. They interact dynamically with Uranus and its ring system. Tidal forces between the planet and its moons may heat their interiors, potentially sustaining subsurface oceans. Ariel, with its bright surface and apparent lack of craters, suggests recent geological activity, while Titania's large canyons hint at tectonic forces that reshaped its surface. Miranda, the smallest of the major moons, features enormous cliff faces and terrain so varied that it looks as though the moon was torn apart and reassembled. Each moon has a story to tell about the processes that shaped Uranus and its surroundings. The magnetic field of Uranus is another enigma. Unlike the relatively aligned magnetic fields of Earth and Jupiter, Uranus's field is tilted and off-center. This irregularity suggests that the dynamo generating the magnetic field is located in a shallow region of the planet's interior, possibly in its icy mantle. Such a configuration challenges traditional models of planetary magnetism and raises broader questions about how magnetic fields are generated in planets of different compositions and sizes. The potential for life on Uranus or its moons is an intriguing prospect, albeit a challenging one to evaluate. While the planet's extreme cold and lack of a solid surface make it inhospitable for life as we know it, its moons may tell a different story. Subsurface oceans, if present, could provide environments where life might exist. These oceans would be shielded from the harsh radiation of space and could contain the chemical ingredients necessary for life, driven by hydrothermal activity or tidal heating. Uranus also provides a unique opportunity to study planetary rings. Unlike Saturn's bright and expansive rings, the rings of Uranus are narrow, dark, and composed of material that absorbs more light than it reflects. Their origin is uncertain. Did they form from the debris of shattered moons, or are they remnants from the planet's formation? The ring's composition and dynamics could reveal new information about the evolution of the Uranian system and the forces that shape ring systems throughout the solar system. As space agencies plan future missions, Uranus emerges as a priority destination. NASA, for instance, has identified Uranus as a high-priority target for exploration in its decadal survey. A mission to Uranus could include an orbiter to study the planet, its rings and moons in detail, as well as an atmospheric probe to dive into its clouds and measure their composition and structure directly. This mission would not only answer questions about Uranus itself, but also pave the way for exploring other ice giants like Neptune, broadening our understanding of this class of planets. In the context of exoplanet research, Uranus serves as a critical benchmark. Many of the planets discovered around other stars fall into size categories similar to Uranus and Neptune, yet these mini-Neptunes remain poorly understood. By studying Uranus in detail, we gain insights that can be applied to these distant worlds. For example, understanding the atmospheric processes of Uranus could help interpret the spectra of exoplanets, revealing their atmospheric compositions and potential climates. Uranus also represents a step toward answering one of humanity's oldest questions. Are we alone in the universe? While the icy moons of Uranus are less well-studied than Europa or Enceladus, they could harbor conditions favorable to life. The discovery of even microbial life beneath the icy crust of a Uranian moon would have profound implications for our understanding of biology and its prevalence in the cosmos. In the grander scheme, Uranus is a reminder of how much there is left to explore. It challenges us to think beyond our familiar world, to push the boundaries of science and engineering, and to embrace the unknown. The mysteries of Uranus are not just puzzles to be solved. They are invitations to expand our horizons, to see the universe in new ways, and to deepen our appreciation for the complexity and beauty of the cosmos. As humanity looks toward the stars, Uranus stands as a gateway to the next great era of exploration. Its secrets, waiting to be uncovered, promise to enrich our understanding of the solar system and inspire generations to come. From its tilted axis to its icy moons and beyond, Uranus is a world that reminds us that the universe is full of wonders, just waiting for us to discover them. The exploration of Uranus is a story that stretches from our earliest understanding of the cosmos to the cutting-edge science of today, with the promise of even greater revelations in the future. To fully appreciate Uranus, we must consider not only what we know, but also the vast realms of the unknown it represents. Realms that invite curiosity, innovation, and a relentless drive to push the boundaries of our knowledge. The formation of Uranus is a mystery deeply tied to the broader evolution of the solar system. Current theories suggest that Uranus, like Neptune, formed in the colder outer regions of the protoplanetary disk, where ices could condense and coalesce into massive planetary cores. These cores, surrounded by lighter gases like hydrogen and helium, eventually became the ice giants we know today. But the exact sequence of events remains unclear. Why did Uranus and Neptune fail to grow as large as Jupiter and Saturn? Was their growth stunted by their position in the disk? Or did interactions with other forming planets scatter them outward, halting their development? Further complicating the picture is Uranus's axial tilt. The prevailing hypothesis is that a collision with a massive body, possibly as large as Earth, knocked Uranus onto its side during its early history. Such an event would have had profound effects on the planet's development, influencing everything from its rotation and internal heat distribution to the formation of its moons and rings. Investigating the scars of this ancient impact, whether through the dynamics of its satellites or the structure of its interior, could provide critical insights into the chaotic processes that shaped the early solar system. Uranus is a planet of extremes, a place where the familiar rules of planetary science seem to bend and break. Its tilted axis, which causes the planet to spin almost on its side, results in a bizarre seasonal cycle. Each pole experiences decades of continuous sunlight followed by decades of darkness, a phenomenon that drastically affects its atmosphere and weather patterns. This tilt is thought to be the result of a massive collision billions of years ago, yet the precise details of this event remain shrouded in mystery. What kind of object could have struck Uranus with enough force to tip it over? And how did such an event shape the planet's evolution over time? The planet's atmosphere, though serene in appearance, hides dynamic processes. Methane gives Uranus its pale blue color by absorbing red light, but beneath this calm exterior lies a chaotic world of storms and winds that reach speeds of up to 900 kilometers per hour. These winds, combined with the planet's extremely low temperatures, the coldest in the solar system, create an atmospheric system that defies easy explanation. Unlike Neptune, Uranus emits almost no internal heat, leaving scientists puzzled about the source of its atmospheric energy. Could the lack of heat be another clue to its tumultuous past, perhaps tied to the same event that tilted the planet? The magnetic field of Uranus is equally perplexing. Unlike Earth's relatively symmetrical magnetic field, Uranus's is wildly tilted and offset from the planet's center. This creates an asymmetrical magnetosphere that twists and bends as the planet rotates, generating unique auroras and interactions with the solar wind. Understanding how this magnetic field is generated could provide insights into the planet's interior, where extreme pressures and temperatures might produce exotic materials like superionic water, a phase of water that conducts electricity like a metal. Uranus is encircled by a system of narrow, dark rings that are both fascinating and mysterious. Unlike the bright and icy rings of Saturn, Uranus's rings are composed of darker material, possibly rich in organic compounds. Their origin is unknown. They may have formed from the remnants of a shattered moon or a captured comet. Studying these rings could reveal not only the history of the Uranian system but also broader truths about the formation and evolution of planetary ring systems throughout the solar system. Beyond the rings, Uranus boasts a collection of 27 moons, each with its own story to tell. Titania and Oberon, the largest moons, show evidence of past geological activity, such as tectonic rifts and impact craters. Miranda, with its dramatic cliffs and varied terrain, appears to have been torn apart and reassembled, suggesting a violent history. Some of these moons might even harbor subsurface oceans beneath their icy crusts, warmed by tidal forces or residual heat. If confirmed, these oceans could provide habitats for microbial life, making Uranus's moons key targets in the search for life beyond Earth. Despite its many mysteries, Uranus remains one of the least studied planets in the solar system. Voyager 2's flyby in 1986 provided the only close-up data we have, and much of what we know about the planet is still based on this brief encounter. However, new technologies and growing interest in ice giants have placed Uranus at the forefront of planetary science. Future missions to Uranus could include orbiters and atmospheric probes designed to study its atmosphere, interior, magnetic field, rings, and moons in unprecedented detail. Such missions would not only answer long-standing questions about Uranus, but also provide critical data for understanding similar planets in other star systems. The importance of Uranus extends far beyond the solar system. Many of the exoplanets discovered in recent years are similar in size and composition to Uranus and Neptune, yet we know relatively little about these types of worlds. By studying Uranus in detail, we gain a window into the conditions and processes that shape ice giants, helping us interpret the data from distant exoplanets and refine our models of planetary formation and evolution. Uranus is a world of contradictions. A cold planet with dynamic winds, a tilted giant with a lopsided magnetic field, and a serene-looking orb that hides a turbulent past. Its exploration represents not just the next step in our understanding of the solar system, but also a journey into the unknown. The secrets of Uranus hold the potential to redefine what we know about planets, not only in our own neighborhood but across the galaxy. Each question we answer about Uranus brings us closer to understanding the fundamental processes that govern the cosmos, reminding us that even the quietest, most distant corners of our solar system are filled with wonder. The journey to uncover Uranus's secrets is a testament to humanity's insatiable curiosity and drive to explore the unknown. While Uranus orbits quietly on the fringes of the solar system, its unique properties and mysteries make it a dynamic laboratory for answering some of the most profound questions in planetary science and beyond. Studying Uranus isn't just about understanding one planet, it's about understanding the broader context of how planets form and evolve. Ice giants like Uranus represent a middle ground between rocky terrestrial planets and massive gas giants, offering a critical missing piece in the puzzle of planetary diversity. By examining Uranus, we can better understand why the planets in our solar system are so different from one another and why planets in other systems seem to exhibit such an incredible variety of sizes, compositions, and orbital configurations. For example, many exoplanets discovered in recent years fall into categories known as mini-Neptunes or super-Earths, which share similarities with Uranus and Neptune in terms of size and possible composition. These planets are among the most common types found in the galaxy, yet they remain poorly understood. Uranus, as an accessible ice giant within our solar system, provides an invaluable analog for studying these distant worlds. Understanding its atmospheric composition, internal structure, and magnetic field could provide the key to deciphering data from exoplanetary systems. One of the most exciting prospects in Uranian exploration lies in its moons. Among the 27 known satellites of Uranus, the 5 largest, Titania, Oberon, Umbriel, Ariel, and Miranda, are especially intriguing. These moons are geologically diverse, with surfaces marked by canyons, craters, and evidence of past tectonic activity. Some even show signs of cryovolcanism, where icy materials erupt instead of molten rock, reshaping their surfaces over time. Titania, the largest moon, is particularly interesting because it may harbor a subsurface ocean beneath its icy crust. If such an ocean exists, it could potentially support microbial life, shielded from harsh radiation and sustained by chemical energy from the moon's interior. Similarly, Ariel, with its relatively smooth surface and bright features, might hold clues to recent geological activity that could also indicate the presence of subsurface liquid water. Miranda, the smallest of the major moons, is perhaps the most visually striking. Its surface is a patchwork of immense cliffs, ridges, and unique formations that appear to be the result of multiple episodes of tectonic and cryovolcanic activity. The origin of Miranda's bizarre terrain remains a mystery, but its study could reveal much about the forces shaping icy moons across the solar system. Exploring these moons could provide critical insights into the potential for life on icy worlds. As scientists increasingly consider subsurface oceans as prime locations for habitability, Uranus's moons offer compelling targets for future missions. They may even rival Europa or Enceladus, moons of Jupiter and Saturn, as candidates for astrobiological studies. Sending a mission to Uranus presents significant engineering and technological challenges. Its vast distance from Earth means that a spacecraft must travel for 10 to 15 years to reach the planet, depending on the trajectory and available propulsion systems. Once there, the spacecraft would need to operate in extremely cold temperatures and communicate across billions of kilometers, with round-trip signals taking nearly 6 hours. Powering such a mission requires advanced systems like radioisotope thermoelectric generators, RTGs, which can generate electricity from the heat produced by radioactive decay. These generators have been successfully used in missions to deep space destinations such as Saturn and Pluto. Additionally, instruments designed to withstand the frigid environment of Uranus would need to be lightweight, robust, and capable of operating autonomously due to the time delay in communications. A future Uranus mission would likely consist of an orbiter and an atmospheric probe. The orbiter would conduct long-term studies of the planet, its moons, rings, and magnetic field, while the probe would descend into Uranus's atmosphere, directly sampling its composition and structure. Together, these components would provide an unprecedented level of detail about the planet and its system. The exploration of Uranus is not just about solving planetary mysteries. It's about pushing the boundaries of human knowledge. By studying this distant world, we gain a deeper understanding of the processes that govern the solar system, from planetary formation to magnetic field generation and the dynamics of icy environments. Uranus also serves as a stepping stone for future exploration of even more distant worlds. Lessons learned from a Uranus mission could inform future missions to Neptune and its largest moon, Triton, a world with an active surface and retrograde orbit that suggests it may be a captured Kuiper Belt object. Beyond Neptune, Uranus could serve as a gateway to understanding the vast, unexplored regions of the outer solar system, including the Kuiper Belt and Oort cloud. In the context of humanity's broader exploration goals, Uranus represents a vital frontier. As we develop the technologies and capabilities to study distant planets, we also prepare for the challenges of interstellar exploration. The knowledge gained from Uranus could one day guide us as we venture beyond the solar system, seeking to understand the countless planetary systems scattered across the galaxy. Uranus reminds us that even in the quietest and most distant corners of our solar system, there are stories waiting to be uncovered. Its tilted axis, icy moons, and dynamic atmosphere are just the surface of the mysteries it holds. Each step toward exploring Uranus brings us closer to understanding not only this enigmatic planet, but also the processes that have shaped the universe itself. As humanity continues to look outward, Uranus stands as a beacon of possibility. Its exploration promises to deepen our knowledge of planetary science, inspire future generations of scientists and engineers, and remind us of the boundless potential of human curiosity. In the silent, icy depths of Uranus lies the promise of discovery, one that could redefine our understanding of the cosmos and our place within it. Uranus is not just another distant planet in the solar system. It is a cosmic enigma waiting to ignite our imagination and challenge everything we think we know about planetary science. It's a world of extremes, contradictions, and mysteries that dares us to explore and uncover its secrets. Imagine standing on one of its icy moons, looking up at the pale blue giant looming in the sky, surrounded by faint rings that whisper of ancient collisions and cosmic drama. This is the allure of Uranus, a planet that is both serene and chaotic, familiar yet utterly alien. Unlike any other planet, Uranus rotates on its side, as if the universe itself decided to defy the norm. This extreme tilt isn't just a curiosity. It transforms the planet into a world of wild seasons where one pole basks in sunlight for decades, while the other endures an equally long, frigid night. Picture this. A single day on Uranus lasts 17 Earth hours, but a year spans 84 Earth years, making its seasons not just long but otherworldly. What would it feel like to experience 42 years of continuous sunlight followed by 42 years of unbroken darkness? This tilt creates conditions we have never seen on Earth or any other planet, making Uranus a natural laboratory for studying extreme planetary climates. Beneath its calm, pastel blue appearance, Uranus's atmosphere is anything but serene. Here, winds howl at supersonic speeds, reaching up to 900 kilometers per hour, 560 miles per hour. These gales sweep across a world that is colder than any other in the solar system, with temperatures plunging to a bone-chilling -224 degrees Celsius, -371 degrees Fahrenheit. How does a planet that emits almost no internal heat sustain such ferocious winds? Scientists are baffled, and the answers could reshape our understanding of atmospheric physics. Uranus's rings, though faint and understated compared to Saturn's, are no less fascinating. They are narrow, dark, and composed of materials so ancient and enigmatic that their very existence poses questions about the planet's violent past. Did they form from the debris of a shattered moon? Are they remnants of the planet's chaotic formation billions of years ago? These rings are like whispers from a forgotten era, waiting for us to decode their secrets. And what could be more thrilling than the possibility of discovering something entirely unexpected? Something no one has imagined. The moons of Uranus are worlds unto themselves, each one unique, each one a mystery. Titania, with its vast canyons and ancient surface, may hide a subsurface ocean teeming with possibilities. Uranus is a planet that defies expectations. Its tilted axis, spinning almost completely on its side, creates a world where the rules we know simply don't apply. Imagine a planet where sunlight bathes one pole for 42 Earth years, while the other plunges into unbroken darkness. This extreme tilt isn't just a feature, it's a signature of a dramatic history. Scientists believe Uranus may have been struck by a massive object in its early life, a collision so catastrophic that it forever changed its orientation. What kind of chaos must have unfolded to leave such a mark? Exploring Uranus is a chance to unravel this cosmic mystery and understand the forces that shaped it. The atmosphere of Uranus is another enigma. At first glance, its pale blue hue seems calm and inviting, but beneath this serene exterior lies a world of ferocious winds and dynamic weather. Winds on Uranus reach speeds of 900 kilometers per hour, sweeping across an atmosphere colder than anywhere else in the solar system, with temperatures plummeting to -224 degrees Celsius. Despite this frigid environment, the planet shows occasional bursts of activity, with bright clouds and storms appearing suddenly. How can such extremes coexist? What powers these mysterious atmospheric events on a planet that emits almost no internal heat? These are questions that only direct exploration can answer. Surrounding Uranus is a delicate system of rings, starkly different from the bright, icy bands of Saturn. These rings are narrow, dark, and composed of material that absorbs more light than it reflects. They are ancient, silent witnesses to Uranus's history, possibly born from the debris of shattered moons or leftover fragments from the planet's formation. Yet, their composition, origin, and evolution remain unknown. What secrets lie in these thin, shadowy bands? Could they hold clues to the violent past of the Uranian system or even broader insights into how ring systems form across the solar system? Beyond the rings lies a collection of moons, each one unique and full of mysteries. The 5 largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, are icy worlds that may harbor hidden oceans beneath their surfaces. Titania, the largest, shows signs of past geological activity, with massive canyons and potential cryovolcanic features. Could its interior still be warm enough to sustain a liquid ocean? Miranda, on the other hand, is a world of extremes. Its surface is a patchwork of cliffs, ridges, and valleys so bizarre it looks like it has been ripped apart and reassembled. What kind of forces created this chaotic landscape? These moons are not just icy rocks. They are potential treasure troves of information about the conditions that may support life in the most unexpected places. Even the magnetic field of Uranus is an anomaly. Unlike Earth's field, which is relatively aligned with its rotational axis, Uranus's magnetic field is tilted at a wild angle and offset from the planet's center. This creates a magnetosphere that twists and warps unpredictably as the planet spins. Studying this field could unlock new understanding about how magnetic fields are generated in ice giants and what role they play in protecting planets and moons from cosmic radiation. Despite its incredible potential for discovery, Uranus remains one of the least explored planets in the solar system. Voyager 2's brief flyby in 1986 gave us a tantalizing glimpse, but it only scratched the surface of what we need to know. Imagine sending a mission designed specifically for Uranus. A spacecraft equipped with advanced instruments to map its atmosphere, study its rings, and explore its moons up close. An atmospheric probe could descend through its thick clouds, directly sampling the gases and revealing the secrets of its composition. An orbiter could spend years unraveling the mysteries of its magnetic field, tracking storms, and capturing stunning images of its moons and rings. Studying Uranus isn't just about understanding one planet. Ice giants like Uranus and Neptune are among the most common types of planets found in other star systems. By exploring Uranus, we gain a crucial reference point for understanding these distant worlds. How do they form? What are their atmospheres made of? Could they host moons with conditions suitable for life? Every discovery we make on Uranus brings us closer to answering these questions on a galactic scale. Uranus challenges us to think beyond what we know. It's a world of contradictions, a cold planet with violent winds, a tilted giant with a lopsided magnetic field, and a serene-looking orb that hides the turbulent past. Its exploration is not just a scientific endeavor. Invitations and depths of Uranus lie answers to some of the most profound the solar system, explore close cosmos, and our place within it. Uranus is a silent giant, patiently waiting on the edge of moons and even the formation of life itself. Its mysteries are not just puzzles to be solved. Ways to a deep and quiet corners of the universe are alive with stories waiting to be. Imagine a mission to the spacecraft humanity's dreams of discovery on a journey spanning more than a decade. As it approaches the ice giant, the first close-up images arrive. Pale blue, its faint rings glowing softly against the blackness of space. The spacecraft begins its work, mapping its atmosphere, first high-resolution images of its moons. Each transmission from Uranus is like a letter from the frontier. Bringing the atmospheric probe descends into the clouds of Uranus. A slow and deliberate plunge, instrument of methane, hydrogen, and helium, revealing subtle variations in temperature and pressure that hint at the planet's complex weather systems. Perhaps it detects unexpected chemical signatures, compounds that challenge our models and hint at processes we've never encountered. The probe's descent is brief, but its discoveries will resonate for decades, shaping our understanding of ice giants and the atmospheres of planets around distant stars. Meanwhile, the orbiter turns its attention to Uranus's moons. High above Titania, it captures images of vast canyons and shimmering icy plains, searching for clues about a potential subsurface ocean. It moves on to Miranda, where towering cliffs cast long shadows across a patchwork surface, a testament to the moon's violent history. Data streams back to Earth, sparking debates and inspiring theories. Could there be hydrothermal activity beneath these moons? Could life exist, hidden beneath layers of ice and rock? The possibilities are staggering. As the spacecraft studies Uranus's rings, it reveals details too fine to see from Earth. The rings, dark and mysterious, may hold answers about the planet's early history. Perhaps they were born from the remnants of a moon torn apart by gravitational forces. Or maybe they're the leftovers of a colossal impact billions of years ago, the same event that tipped Uranus onto its side. Each fragment of ring material tells a story, each orbit a chapter in the history of the Uranian system. This mission isn't just about data. It's about rekindling humanity's sense of wonder. Uranus challenges us to look beyond the familiar, to embrace the unknown with open minds and daring questions. It reminds us that the universe is not static but dynamic, filled with surprises that defy our expectations. But Uranus also connects us to something greater. Its exploration is a celebration of human ingenuity, a testament to our ability to ask big questions and seek answers in the vastness of space. It is a reminder that even in a universe filled with billions of stars and countless planets, each world is unique, each story worth hearing. As we dream of Uranus, we dream of what comes next. Exploring its moons could prepare us for missions to Europa or Enceladus, where the search for life takes center stage. Studying its rings could inform future missions to Saturn or exoplanetary systems with similar structures. Understanding its magnetic field could reveal how planetary shields protect, or fail to protect, moons and atmospheres from solar and cosmic radiation. Uranus is not just a destination. It is a stepping stone, a bridge to the future of planetary exploration. It challenges us to imagine, to innovate, and to keep reaching for the stars. And as we take those steps, we carry with us the unshakable belief that every mystery, no matter how distant, is within our grasp if we dare to explore. This is the promise of Uranus, a world that waits quietly, holding answers to questions we have not yet dared to ask. It calls to us, not with loud proclamations, but with the soft, persistent whisper of the unknown. And as we listen, as we explore, we become not just observers of the universe, but participants in its grand and unfolding story. The scientific potential of Uranus goes far beyond its captivating visuals and dramatic features. It stands as a crucial testbed for understanding the processes that govern not only the formation and evolution of planets within our solar system, but also the myriad of exoplanets discovered across the galaxy. Uranus is a natural laboratory for studying extreme physics, atmospheric dynamics, magnetic field generation, and the interactions between moons, rings, and their host planets. Each of these domains offers invaluable insights that ripple out to broader questions in planetary science, astrophysics, and even astrobiology. Uranus's atmosphere is unique in its composition and behavior. It consists primarily of hydrogen and helium, with about 2% methane, which absorbs red light and gives the planet its characteristic blue-green hue. Beneath this seemingly calm surface lies a world of intricate dynamics. Winds at supersonic speeds whip around the planet, and bright cloud systems occasionally appear, suggesting active, though poorly understood, weather patterns. The planet's extreme cold, with temperatures dropping as low as -224 degrees Celsius -371 degrees Fahrenheit, makes it the coldest planetary atmosphere in the solar system. Unlike other giant planets, Uranus emits almost no detectable internal heat. This lack of heat flow creates a thermal environment vastly different from Jupiter, Saturn, or Neptune. Studying the atmosphere of Uranus could reveal why its thermal behavior is so anomalous and whether this is linked to its unusual tilt or early formation history. Further investigation into Uranus's atmosphere could also illuminate the chemistry of ice giant exoplanets. Methane dominates the upper layers, but deeper within, ammonia, hydrogen sulfide, and water may form clouds under immense pressure. These conditions provide a model for understanding atmospheric chemistry on distant worlds with similar compositions, helping scientists interpret spectral data from exoplanet observations. Uranus's magnetic field is one of the most irregular in the solar system. Unlike Earth's magnetic field, which is roughly aligned with its rotational axis and originates from a deep core dynamo, Uranus's field is tilted by 59 degrees relative to its axis and offset from the planet's center by about a third of its radius. This produces an asymmetrical magnetosphere that changes dramatically as the planet rotates, creating dynamic interactions with the solar wind. This lopsided magnetic field is thought to originate in a thin shell of ionic slush within Uranus's icy mantle, rather than from a molten core. Studying this field can provide critical insights into how magnetic fields form and behave under different planetary conditions. Understanding Uranus's magnetosphere could also offer clues about how magnetic fields protect, or fail to protect, atmospheres and surfaces from space weather, a question with direct implications for the habitability of exoplanets. The interior of Uranus is composed of a rocky core surrounded by a dense, icy mantle of water, ammonia, and methane, all compressed under extreme pressure and temperature. Recent models suggest that exotic states of matter may exist within this mantle. One such state is superionic water, where oxygen atoms form a crystalline lattice while hydrogen ions flow freely, behaving like a liquid metal and conducting electricity. This superionic phase could play a key role in generating Uranus's magnetic field, as well as influencing its thermal properties. Further study of these extreme states of matter could have applications far beyond Uranus, providing insights into high-pressure physics relevant to other planetary interiors, from Neptune to massive exoplanets. The rings and moons of Uranus represent a microcosm of planetary interactions. Uranus's rings, composed of dark, radiation-processed material, are faint and narrow, contrasting sharply with the bright, icy rings of Saturn. Their composition and origin remain enigmatic. Do they represent the remnants of a shattered moon or the primordial building blocks of Uranus's system? Understanding the dynamics of these rings could illuminate how ring systems evolve over time and how they interact with moons and planetary magnetospheres. The moons of Uranus are equally compelling. The 5 largest moons, Titania, Oberon, Ariel, Umbriel, and Miranda, are icy worlds with diverse geological features, including canyons, impact craters, and evidence of resurfacing. These moons may harbor subsurface oceans, particularly Titania and Ariel, where heat from tidal forces or radioactive decay could maintain liquid water beneath an icy crust. If confirmed, these oceans could represent potential habitats for life, offering a critical piece in the broader search for habitable environments in the solar system. Miranda, the smallest of the major moons, is particularly intriguing. Its surface features dramatic cliffs and chaotic terrain that suggest a history of extreme tectonic and possibly cryovolcanic activity. Its irregular shape and surface composition could hold clues to the processes that shape icy bodies in the outer solar system. As we uncover more about Uranus, it becomes increasingly clear that it serves as a proxy for understanding the thousands of ice giants and mini-Neptunes discovered orbiting other stars. These exoplanets, often found in close orbits around their host stars, display a wide range of atmospheric compositions and dynamics. Uranus provides a tangible example for calibrating models of exoplanetary atmospheres, helping astronomers interpret the data collected by telescopes like the James Webb Space Telescope. By studying Uranus, scientists can refine their understanding of planetary formation, particularly how and why planets like Uranus and Neptune differ so dramatically from gas giants like Jupiter and Saturn. This research has implications for understanding the distribution of planetary types in the galaxy, the conditions under which they form, and their potential to host moons or rings that could influence their habitability. Despite its scientific importance, Uranus remains largely unexplored. Voyager 2's flyby in 1986 provided valuable data, but it only scratched the surface. A dedicated mission to Uranus is essential to unlock its secrets. Such a mission could include an orbiter, equipped with instruments to study the planet's atmosphere, magnetic field, and ring system over an extended period, an atmospheric probe, designed to descend into Uranus's atmosphere and directly measure its composition, pressure, and temperature. A moon explorer, focused on studying the largest moons, searching for evidence of subsurface oceans, and mapping their geologic features in detail. The technologies required for such a mission long-duration spacecraft, advanced power systems like radioisotope thermoelectric generators and autonomous navigation, are within reach. With proper investment, a Uranus mission could launch within the next decade, offering humanity its first detailed look at an ice giant and its dynamic system. Uranus is more than a distant planet. It is a cosmic laboratory that challenges our understanding of planetary systems. Its exploration promises to answer fundamental questions about planetary formation, magnetic fields, atmospheric dynamics, and the potential for life in unexpected places. As we take our first steps toward exploring this enigmatic world, we embark on a journey that could reshape not only our understanding of Uranus but also the very nature of planets across the galaxy. Uranus remains one of the most enigmatic worlds in our solar system, a place where the expected norms of planetary science break down. The more we learn, the more questions arise, each one more tantalizing than the last. Its pale blue hue, a result of methane in the atmosphere, masks a complexity that scientists are eager to unravel. The planet's lack of significant internal heat is a puzzle. Why does Uranus emit so little energy compared to its neighbor Neptune? Both are ice giants, yet Uranus appears cold and subdued, while Neptune showcases more dynamic atmospheric activity. This contrast hints at fundamental differences in their internal structures or histories, and understanding Uranus could illuminate what makes ice giants unique among planetary classes. The extreme tilt of Uranus, which results in its poles facing the Sun during parts of its orbit, produces bizarre seasonal effects. Entire hemispheres are plunged into decades-long darkness, followed by equally long periods of continuous daylight. How does such an extreme orientation affect atmospheric circulation and weather patterns over time? Observations show that despite its subdued appearance, Uranus occasionally experiences massive storms and cloud formations, likely triggered by these unusual seasonal transitions. Studying these events can provide a deeper understanding of how energy flows in a planet's atmosphere when external sunlight becomes the dominant driver, as opposed to internal heat. The planet's moons, particularly Titania and Oberon, are icy worlds that may harbor some of the most compelling environments for astrobiology in the outer solar system. Subsurface oceans, kept liquid by residual heat or tidal forces, could exist beneath their frozen surfaces. These oceans might contain dissolved organic compounds, creating a potential habitat for microbial life. Future missions to Uranus could use radar or other instruments to penetrate the icy crusts of these moons, searching for signs of liquid water or geochemical activity. Discovering life or even the building blocks of life on one of these moons would be one of the most profound scientific achievements in history, reshaping our understanding of habitability. Miranda, the smallest of Uranus's major moons, stands out as a geological marvel. Its surface features enormous cliffs and regions that appear as though the moon was shattered and pieced back together. This chaotic terrain suggests a violent history of tidal interactions or cryovolcanic processes that reshaped the surface over time. Studying Miranda up close could reveal how such processes operate on small, icy bodies, providing insight into the evolution of moons throughout the solar system. The magnetic field of Uranus is another extraordinary feature. Unlike Earth's field, which is generated by a molten iron core and aligns closely with the planet's rotation axis, Uranus's magnetic field is wildly tilted and offset from the center of the planet. This creates an unusual and dynamic magnetosphere, with complex interactions between the solar wind and the planet's magnetic environment. Observing how this field behaves and how it interacts with the rings and moons of Uranus could offer new insights into the mechanisms of magnetic field generation, not only on Uranus but on other planets, including exoplanets. The rings of Uranus, though less dramatic than Saturn's, hold their own mysteries. They are dark, narrow, and composed of material that appears ancient. Their composition and structure could provide clues about the early history of the Uranian system, including the violent events that may have shaped the planet and its satellites. Do these rings represent remnants of a moon destroyed by tidal forces, or are they debris left over from Uranus's chaotic formation? Future missions equipped with high-resolution imaging and spectrometers could analyze the rings in unprecedented detail, revealing their age, composition, and origin. Uranus also serves as a critical reference point for understanding exoplanets. Ice giants are among the most common types of planets found in other star systems, yet they remain poorly understood. By studying Uranus, scientists can develop models to better interpret observations of distant worlds with similar masses and compositions. This has implications for understanding planetary atmospheres, interiors, and even the potential for moons or rings around exoplanets. Sending a dedicated mission to Uranus is not just about solving these mysteries. It's about opening the door to a deeper understanding of planetary systems as a whole. An orbiter could spend years studying Uranus's atmosphere, rings, and moons, while an atmospheric probe could dive into its clouds, directly sampling their composition and structure. Such a mission would revolutionize our understanding of ice giants and provide a wealth of data for comparative planetology. The technology to explore Uranus is within reach. With advancements in propulsion power systems like radioisotope thermoelectric generators and autonomous spacecraft operations, we are on the cusp of being able to study this distant world in detail. The results could redefine what we know about not only our solar system but the countless planetary systems scattered across the galaxy. Uranus is a reminder that even the quietest, most distant corners of our cosmic backyard are filled with wonders. Its exploration represents a bridge between what we know and what we have yet to discover. It challenges us to ask deeper questions, to push the limits of our technology, and to embrace the unknown with the same curiosity that has driven humanity to explore since the dawn of time. As we look toward Uranus, we are not just seeking answers about one planet. We are reaching for a deeper connection with the universe itself. The study of Uranus is a profound exercise in pushing the boundaries of what we know about planetary science and the mechanics of our universe. It's a planet that holds answers to questions we've only begun to ask. How do ice giants form? Why do some planets retain heat while others, like Uranus, lose it so rapidly? What unique atmospheric processes can arise when a planet lacks significant internal energy? Each of these questions is a thread, and Uranus is the tapestry waiting to be unraveled. The planet's distance from the Sun, combined with its lack of heat emission, means that almost all of its atmospheric energy comes from solar radiation. This makes it a natural laboratory for studying how a planet's atmosphere behaves under such conditions. The supersonic winds, for instance, suggest an efficient mechanism for redistributing heat despite the planet's limited energy sources. What drives these winds? How do they interact with Uranus's uniquely tilted axis and seasonal extremes? Answering these questions could refine our understanding of atmospheric dynamics, not just for Uranus but for other planets, including Earth. Uranus's interior, hidden beneath its hazy atmosphere, is another puzzle. Current models suggest a rocky core surrounded by a thick, icy mantle made up of water, ammonia, and methane. Under the immense pressures and temperatures found inside the planet, these ices don't behave as they do on Earth. Instead, they may form exotic phases like superionic water, where hydrogen ions move freely through an oxygen lattice, creating a conductive material. This state of matter could be responsible for the planet's irregular magnetic field. Studying these conditions could have far-reaching implications, helping us understand not only Uranus but also the internal dynamics of ice giant exoplanets. The potential for subsurface oceans on Uranus's moons adds another layer of intrigue. If oceans exist beneath the icy crusts of moons like Titania and Oberon, they could provide a stable, energy-rich environment capable of supporting microbial life. These oceans would likely be warmed by residual heat from the moon's formation or by tidal interactions with Uranus. If life exists in these hidden oceans, it would represent an entirely different biosphere, independent of sunlight and reliant on chemical energy. Such a discovery would fundamentally reshape our understanding of life's potential in the universe. The exploration of Uranus could also provide critical insights into the formation of its ring system. The rings are sparse and dark, composed of material that appears ancient. Are they remnants of a moon destroyed by tidal forces? Or are they leftovers from Uranus's chaotic formation? By analyzing their composition and dynamics, we could learn more about the processes that govern the formation and evolution of planetary ring systems across the solar system. Another compelling aspect of Uranus is its role as a key to understanding exoplanets. Many of the planets discovered in other star systems are similar in size and composition to Uranus, yet we lack a clear understanding of these worlds. Uranus is the only ice giant within reach of detailed study, making it a vital benchmark for interpreting data from exoplanetary systems. By studying its atmosphere, magnetic field, and interior, we can develop models that apply to the thousands of ice giants and mini-Neptunes found in our galaxy. Technologically, a mission to Uranus represents the next great challenge in planetary exploration. The vast distance of over 2.8 billion kilometers from the Sun requires innovations in spacecraft propulsion, energy generation, and autonomous operations. However, the rewards far outweigh the challenges. A dedicated Uranus mission could transform our understanding of ice giants, paving the way for further exploration of Neptune, its dynamic moon Triton, and beyond. The data collected from Uranus would also deepen our understanding of the early solar system. Uranus likely formed in a region rich in ices and volatiles, which played a crucial role in shaping its composition. As it migrated outward to its current position, interactions with other planets could have sculpted its unique features, from its tilted axis to its complex system of moons and rings. By piecing together this history, we gain insights into the chaotic processes that shaped not only Uranus but also the solar system as a whole. Uranus challenges us to think big, to imagine possibilities far beyond our current knowledge. It's a world that holds the keys to understanding planetary formation, the behavior of atmospheres and magnetic fields, and the potential for life in the most unexpected places. As we prepare for the next generation of space exploration, Uranus stands as a reminder that the greatest discoveries often come from the most distant and quiet places. It's a silent giant, waiting to teach us more about the universe and about ourselves. Uranus is not just a planet. It's a cosmic mystery, a scientific treasure chest that begs to be unlocked. It defies expectations at every turn, challenging our understanding of how planets form, evolve, and interact with their surroundings. The more we think about Uranus, the more we realize how much there is to learn, not just about the planet itself but about the nature of planetary systems across the universe. Let's consider the incredible implications of Uranus's magnetic field. The fact that it is tilted and offset from the planet's center suggests that it is generated in a completely different way than Earth's or even Jupiter's. Imagine what this tells us about the inner workings of ice giants. Could Uranus's magnetic field offer clues about magnetic activity on other planets, including those we might one day explore in other star systems? And what about the effect of this magnetic field on Uranus's moons and rings? Every orbit and every interaction could be subtly influenced by this invisible force, creating dynamic relationships we have yet to fully understand. And then there's the question of how Uranus's tilt affects its internal dynamics. If a massive collision knocked Uranus onto its side, it's possible that this event fundamentally altered the planet's internal structure. Layers of icy materials might have been reshuffled, with denser substances sinking toward the core and lighter ones rising toward the surface. Could this explain why Uranus emits so little heat compared to other giant planets? Did the collision somehow lock Uranus into a cold, stagnant state? Or is there something deeper at play? The tilt also has fascinating consequences for the planet's moons. Unlike Jupiter or Saturn, where the equatorial plane is closely aligned with the orbital plane of the moons, Uranus's moons orbit along its tilted axis. This creates a system where the gravitational interactions between Uranus and its moons operate in ways we've never observed elsewhere. These interactions could influence everything from the moon's orbits to the potential for subsurface oceans. Imagine what we could learn by studying these unique tidal forces and their effects on the moon's geologies. The rings of Uranus, though faint and narrow, are a marvel of stability in a chaotic environment. Despite the planet's tilted axis, the rings remain aligned with its equatorial plane, a testament to the delicate balance of gravitational forces at work. Yet their composition remains a mystery. Are they made of organic-rich materials? Could they contain frozen volatiles or even complex carbon compounds? If we could analyze the composition of these rings, we might uncover clues about the chemistry of the early solar system. And let's not forget the tantalizing possibility of life. While the icy crusts of Uranus's moons may seem inhospitable, their hidden oceans could be a different story. These subsurface seas might be warmed by tidal forces or radioactive decay, creating an environment where life could potentially exist. If we found even the faintest trace of microbial life in these oceans, it would be one of the most profound discoveries in human history. It would confirm that life can emerge in conditions vastly different from those on Earth, broadening our understanding of habitability in the universe. Uranus also holds the key to understanding the most common type of planet in the galaxy, the ice giant. Thousands of exoplanets have been discovered that are similar in size to Uranus, yet we know so little about what these planets are like. Are their atmospheres dynamic, like Neptune's, or subdued, like Uranus's? Do they have rings and moons? Are they rich in volatile compounds like water, ammonia, and methane? Uranus is the perfect stepping stone for answering these questions, allowing us to compare its behavior to that of distant worlds light years away. A mission to Uranus would be a journey into the unknown, Imagine the thrill of descending through its atmosphere with a probe, sampling gases that have been untouched for billions of years. What secrets lie within those clouds? Could we find unexpected compounds that challenge our models of planetary chemistry? And what about the thrill of orbiting the planet, capturing breathtaking images of its moons and rings as they slowly drift in the alien light of a distant sun? The scientific rewards of such a mission would be immense, but the emotional and cultural impact would be just as profound. The exploration of Uranus would remind us of the boundless potential of human curiosity and ingenuity. It would inspire a new generation of scientists, engineers, and dreamers to look up at the night sky and wonder what else is out there. Uranus is a planet of contradictions. A cold, distant world with violent winds. A serene-looking orb with a chaotic history. A quiet giant that holds answers to some of the biggest questions in science. It is a world that challenges us to think bigger, to explore farther, and to embrace the mysteries of the universe. As we stand on the cusp of a new era of space exploration, Uranus calls to us, inviting us to uncover its secrets and, in doing so, learn more about ourselves and our place in the cosmos. Uranus holds secrets so profound and so strange that each discovery could fundamentally alter how we perceive planets, both within our solar system and across the galaxy. This silent, icy world, tilting at a 98-degree angle, is a cosmic anomaly in every sense, defying expectations and inviting us to dive deeper into its mysteries. To explore Uranus is to explore the unexpected, where every feature, from its bizarre magnetic field to its dark, ancient rings, challenges what we thought we knew about planetary science. Let's begin with its tilted rotation, which isn't just unusual, it's unprecedented. Uranus doesn't merely tilt. It lies almost entirely on its side, spinning like a rolling ball around the sun. This extreme tilt creates a world of unimaginable seasonal extremes. Picture one pole bathing in unbroken sunlight for 42 Earth years, while the other is locked in a freezing darkness. Such extremes fundamentally reshape the dynamics of a planet's atmosphere. How does this bizarre orientation influence the chemistry and circulation of Uranus's atmosphere? Could these conditions lead to atmospheric phenomena never before observed on any other planet? And then there's the mystery of its heat, or lack thereof. Uranus radiates almost no internal heat into space, making it the coldest planet in the solar system. This sets it apart from every other giant planet, including Neptune, which, despite being nearly as far from the Sun, emits significantly more internal energy. What could explain Uranus's frigid demeanor? Could the ancient collision that knocked it sideways have also disrupted its core, dispersing its heat into space billions of years ago? Or is there an unknown process within Uranus's icy mantle that traps heat, preventing it from escaping? Uncovering the cause of this cold anomaly could rewrite our understanding of planetary thermodynamics. The winds on Uranus are equally perplexing. Despite its lack of internal heat, the planet boasts some of the fastest winds in the solar system, reaching speeds of up to 900 kilometers per hour, 560 miles per hour. These winds tear across a world where temperatures drop to an almost incomprehensible -224 degrees Celsius -371 degrees Fahrenheit. How do these supersonic gales form in such a frigid, energy-starved environment? The answer could hold clues to the atmospheric dynamics of not just Uranus but also exoplanets with similar conditions. Its magnetic field adds yet another layer of wonder. Unlike Earth's symmetrical, stable magnetic field, Uranus's is tilted 59 degrees from its axis and offset from the planet's center by nearly a third of its radius. This produces a chaotic magnetosphere that twists and warps unpredictably as Uranus rotates. Imagine a spacecraft flying through this ever-shifting magnetic field, capturing data about its interactions with the solar wind. What secrets could this magnetic anomaly reveal about the planet's interior and the generation of magnetic fields in ice giants? The rings of Uranus, though faint compared to Saturn's, are steeped in mystery. These narrow, dark rings are made of material so ancient that they may predate the moons orbiting the planet. Could they be remnants of a moon torn apart by gravitational forces? Or are they primordial debris left over from Uranus's formation? And what about their composition? Are they rich in complex organic molecules, hinting at the chemical processes that shaped the early solar system? Studying these rings in detail could unlock a chapter of cosmic history that has remained hidden for billions of years. And then there are the moons, a system as diverse and intriguing as any in the solar system. Titania and Oberon, the largest moons, are icy worlds marked by massive canyons and impact craters. Yet beneath their cold, cratered surfaces could lie vast oceans of liquid water, kept warm by tidal forces or residual heat from their formation. If these oceans exist, they could be chemically rich, creating environments where life might emerge. Imagine discovering even the faintest signs of microbial life on a moon orbiting Uranus. It would forever change our understanding of life's resilience and its potential to thrive in the most unexpected places. Miranda, the smallest of Uranus's major moons, is perhaps the most bizarre. Its surface is a chaotic mosaic of cliffs, valleys, and ridges, some of which are 20 kilometers, 12 miles, high, the tallest known in the solar system. Miranda's terrain looks like it was torn apart and reassembled in a cosmic puzzle. Could this be the result of tidal heating,